觉得是种。看到。Yeah, well, I think I would assume so. But something just very long as you find the point place that I was just on. That when you Hey, on. Hello. Oh, okay. Well, I'm not taking tree phone. I don't know. We have a rule. Yeah. You from home. Hey, probably. I don't know. Good thing we're crazy.
I know, I was ready with my scarf jacket, and it's actually comfortable.
Yeah, it took me all the way.
I know, it's first, right?
Yeah. I would say I just have to do good with it.
All right, good. Well, want to first thank everybody, especially our outside participants for taking the trip to Minnesota for this workshop beyond frontiers beyond the standard model 4. Some of you, maybe a number of you have been here for some of the previous editions of this workshop, but it's been a while since we've had it. So we're glad to be able to resume it. Hopefully it'll see days. Just want to mention that the workshop is sponsored by the Resistance Team. So that's what makes all of this possible. And in addition, Science Foundation grant also helped out take the workshop. So with that, I think things are pretty straightforward. We'll have quite a number of talks, but I think it'll be very interesting. And I just want to mention that, for things like lunches, you're all on your own for lunches, but there's plenty of places in the university here along Washington Avenue. There's also on the workshop website, there's a link for. So with that, we can get started, and the first talk is by Raman Syndrome. And the title, if I remember it, is Symbiosis between Supersymmetry and Composite. Mostly you come best.
Do I need this or?
Nah.
Okay.
They're recording call, no? Probably.
Are they recording it?
So this is work on.
You told them not to record it.
Well.
Okay, I'm sorry.
Okay.
This is work I'm doing with Cosmological today, and the crowd of Popsy, and sort of ongoing, just give you the status report. I mean, in some way, we're
Yeah, I uploaded a talk, I uploaded an alternate talk. But you do it on your laptop. Oh, I can do it on my laptop, yeah. So.
No.
Well, we're uploading some data.
Oh, well, maybe it's.
No, it's okay.
But do we know where it is?
I put it in your Google.
Oh, no, that's. I'm supposed to delete all this. See you guys.
That's
A mí lo que tengo aquí debe estar dos.
Yes, for all the speakers here, we're gonna have to just bring up your laptop, that's how we're gonna do. No, there isn't. Now we can keep it full screen.
Yeah, I don't know.
It should be. Alright, so our next talk is by David Kaplan about messing around with. Messing around with field theories or gauge theories without constraint.
Or, yeah. Shoot, I shouldn't use this. Simon, I realize how loud I am. Okay. Yeah, so I hate this. Mark Kimikowski once did this. He came after we hired him. He gave a talk which started with 6 optional talks, and the audience could choose which talk.
You were very judgy about that.
Here I am now, yes, from Mary Tyler Moore to the current political situation in the United States.
What did he choose?
Sublime to ridiculous.
What did he choose, or what did you?
Oh, we voted, I think we chose, he had 8 options, we saw 3 of them. I can't remember what they were. Okay, so I can either give this talk, which is very polished, and some of you have seen versions of it, and it's messing around with field theory. Or I can give a talk, which the only version of I've ever given was to Raman and Anson and Kaustubin and John and Ricardo, who yelled at me afterwards the whole time, about using nonlinear quantum mechanics to solve the hierarchy problem. That work is not finished. I don't know if it works. I give it about a 50–60% chance of being able to solve the hierarchy problem that way. We address some of the issues. It's 11 slides. This is a full talk that talks about potentially how to get dark matter without new fields.
Just for the record, I didn't yell at you.
Ricardo, just Ricardo.
That's not unusual.
No, it's true. He comes in yelling, yeah. I need something to tip the scale. Help.
Dark matter.
Figured. Seth, Mary Tyler Moore. Okay. Gauge theories without constraints. So this is just a playful thing you can do. Go back to your old textbooks or Jakeev lectures, things like that, and think about how to quantize gauge theories. And it is always going to be in the Hamiltonian perspective, the canonical quantization from the beginning. And what we know is that if we believe the Hamiltonian construction in Hilbert space, that we need to construct a Hamiltonian in Hilbert space that reproduces the classical physics, GR, electromagnetism, Newton's laws in general. And so here I'm just going to explore building a Hamiltonian for electromagnetism and gravity, for which some of the predicted classical stuff is different. But the dynamics of these theories are the same as Maxwell's equations in GR. So let's start with a little toy. The classical equations of motion come from a quantum theory by first building a classical action, and we know minimization of a classical action is what dictates the equations of motion. And so this is, we can get Newton's laws out of something like this. We build the correct Lagrangian. And for a Hamiltonian, classically, we define conjugate momenta, which we have a prescription to do, and perform a Legendre transform to get the classical Hamiltonian. Now, Ehrenfest's theorem is simply a statement that if you turn your x and p's into operators and give them non-trivial commutation relations, then from the Schrodinger equation, you can get the equations of motion that look very classical. In other words, time derivative of, say, the expectation value of the x operator will give you that x dot is p over m, and similarly, expectation value of the p operator, time derivative, gives you f equals ma. And so all you have to do is choose a quantum Hamiltonian that generates the classical equations of motion you want in expectation value. Now let's look at a simple example. 2 particles that interact with each other have some mutual potential, but there's no background potential. So in this case, we can go to center of mass coordinates. We can redefine the operators in such a way that the Hamiltonian now depends on 2 things: a pair of conjugate variables, the relative position and its conjugate momentum, and a center of mass momentum p, where the center of mass doesn't appear, of course, in the Hamiltonian. Center mass not appearing in the Hamiltonian means that the center mass momentum, of course, commutes with the Hamiltonian, and that means it's a conserved quantity or represents something that when set doesn't change in time. So I could just say that quantum state I'm in is an eigenstate of the total momentum operator, and it has some eigenvalue p. I can't measure it in this theory. This is nothing that couples to that p. It's just something that can label the states. We can think of these eigenstates of the total momentum as super selection sectors, meaning you can't get from one to the other. You can't break total momentum conservation in this theory. We don't know what sector we live in this world. It could be total momentum is zero, total momentum is some constant. It could be that the initial state of the universe is in some linear combination of all momenta. There's some spread in the total momentum. We don't know, can't measure it. Those are all options, and that broadly defines the Hilbert space. I could add a term that does depend on that total momentum and say it's that total momentum multiplying a different potential function for the relative coordinate q. It's still true that the total momentum commutes with the Hamiltonian. So in that sense, the total momentum is a conserved quantity. We could live in this sector or in this sector or some linear combination. And now, however, measurement allows us to find out what superselection sector we're in. So even though P still commutes with the Hamiltonian, there are observables, which is the potential for Q, that tells us what value of P we're in. And if we're in this situation where the initial state could be lots of linear combination of total momentum, then by measuring the potential for Q, we entangle ourselves with that value of P. Does that make sense?
Yeah.
Thanks, Ron. I'm only giving the talk here. Speak. Thank you. Everybody agree? All right, classical electromagnetism. We write down the action. We know how to get Maxwell's equations. We simply minimize the action with respect to field configurations of the vector potential A0, and the spatial vector potential AI. And when we do that, minimizing, we get Gauss's law and Ampere's law. And now we can ask, all right, I want to get to the Hamiltonian version of this story. Let me write down the conjugate momenta. And the conjugate momentum for a vector is what we call the electric field, but it has a set of conjugate momenta. And for A0, of course, since A0 dot does not appear in the action, there's no conjugate momentum. And now you have to make a decision about what to do in the quantum theory. You can classically write down a Hamiltonian density, which looks like this, where now to do my Legendre transform, I didn't have a conjugate momentum for A0, so I simply allowed it as some background field. And when I want to make this a quantum theory, I can make a decision about what to do with A0. In fact, the classical theory has this gauge symmetry, and now I have some game I can play. I can choose a gauge, which really means choosing the definition of some of the operators here, knowing now after decades of careful work in path integral language, etc., we know that these theories generate physically the same physics. And so I'm going to use that freedom and simply take A0 equal to 0, which is the Weyl gauge or temporal gauge. I like this gauge because the commutators are totally canonical in this case. You go to Coulomb gauge, you have some crappy extra terms. But here we have just the specific three fields and their conjugates appearing in the Hamiltonian. And now, classical physics. How do we get classical physics out? We take derivatives of expectation values, and we find that A dot is equal to E, as we wanted in the first place. Sign. And then E dot is just equal to del cross B plus J. That is simply a result of this commutation relation. So an expectation value, we get Ampere's law, and one can ask, well, what about Gauss's law? We lost A0, so it doesn't automatically come from Schrodinger's equation. However, beautifully, Gauss's law commutes with the Hamiltonian, which means I can set it as an initial condition on my states. And now I have Gauss's law, a sort of different version of the laws of nature of Maxwell's equations. Here, Ampere's law is satisfied in expectation value, whereas Gauss's law is an explicit eigenstate of the longitudinal part of the electric field, or some combination of that and charge matter. This is how we get classical electromagnetism out of the Hamiltonian language of quantum electromagnetism, or QED. Now, of course, what you see, as I talked about in the case of a particle, is we could take another initial condition. We could simply say that the state the universe starts in is an eigenstate of the Gauss's law operator, but it is a non-zero eigenvalue. Some function of space, it must not be a function of time since G commutes with the Hamiltonian. Or even we could say the initial state of the universe is some linear combination of these eigenstates, say that they're centered around zero. So in expectation value, we got Gauss's law, or even in expectation value, we get some thing, some function of space. And physically, we would say that function of space is just simply a background charge. Because again, now the expectation value of some quantity, which looks like Gauss's law operator minus this function, is equal to zero. And so what would this look like in the physical world? We'd say, oh, we see some background charge density. Perhaps it's a super heavy particle, and they were just distributed through the universe. We don't know why. They're so heavy, we can't move them. And so we see them as a background charge density. In that language, you see that quantum mechanically or the quantum field theory, nothing goes wrong. We're just quantizing around this classical background. When I say nothing goes wrong, I mean, for example, the photon has a pole at p squared equals 0. There's a massless photon with transverse modes. Two of those, sorry. Okay, gravity. What's the timing situation since the audience took so long in his talk?
You've got about 13 minutes or so.
13
We're
minutes.
going to.
All right, let's go
You
straight
can
to
talk
GR.
till, when the big hand hits the 7, that's when you should stop.
That's how I speak to my child.
Kids are grown up.
I know he's slower, but it's still. All right. GR. How do we do GR? Well, we could take again the classical action for GR, the Einstein-Hilbert action, plus some Gibbons-Hawking-York term to get rid of the second derivative terms. And classically, how do we get the equations of motion? We again vary the action with respect to the degrees of freedom, g mu nu. And in varying that and setting it equal to 0, we get something that looks like Einstein's equation. Einstein's equation times square root of minus g. And so it makes sense at square root of minus g equals 0 anyway, so we're happy with that. What are the conjugate momenta? 6 of the parts of the metric Gij have conjugate momenta. 4 parts of the metric don't appear with a time derivative, and so there are no conjugate momenta for those 4. Now, what do? To get a Hamiltonian, I'm going to pick a gauge. I'm going to decide what to do with those components. And the simplest gauge is the synchronous gauge, in which the 0,0 component is -1 and the 0i component is 0. I like this gauge because it doesn't mix time and space. It allows me to think about the Schrodinger equation independently of the other interaction terms within the Hamiltonian. And so the spatial parts of the metric, which I'll call gamma ij, they have conjugate momenta. I can now pose quantum mechanically that the fields have the standard commutation relations. And when I do that, I can build a Hamiltonian. Hamiltonian has a kinetic term for those 6 Gij. It has gradient terms for the 6 Gij, and then has contributions from matter coupling to gravity. There are six fields still here, but when we get to the dynamical equations, 2 of them have real dynamics. They have gradient terms, and 4 of them are constraints. So the equations of motion you get out from Ehrenfest's theorem, which is time derivative of expectation values, written just back in terms of the fields, you get the spatial part of Einstein's equations. The remaining equations, so this is under the rug. Whenever we do sort of the classical limit, we're taking coherent states. And there's some subtleties about operator ordering, which I will not talk about. The remaining constraints, the remaining equations that we get classically are constraint equations. And those constraint equations are on what are called the momentum and Hamiltonian operators, or the Hamiltonian momentum constraints. And if we set those as expectation values on those constraints, we get in expectation value the remaining classical equations of motion. And now you can ask, well, what if I do something different with that constraint? What if I, in this gauge, in this language, I'm starting with quantum theory, I give expectation values which are non-zero, some non-zero functions to the Hamiltonian constraint and to the momentum constraints. And all that would do is produce some field or object or function on the right side of those constraints. So in general relativity, we'd have our classical limit equations, which look like the normal Einstein equations, but with some extra source terms. And if I divide by that square root of minus g, I'll get source terms which contain the metric itself. And I can package those in this particular gauge in a tensor. And that tensor looks like this. It has 0 in the spatial parts, and then it has off diagonal and a 0, 0 component. And here I've made explicit the square root of minus g, and in this gauge, in principle, those are arbitrary functions. Well, they're not totally arbitrary, because if you look at this set of 10 equations, the left side of this 10 equations just satisfies the Bianchi identity, which is d mu g mu nu equal to 0. That's simply a relationship between the various parts of the metric in there. On the right side, the equations of motion of the matter dictate that d mu t mu nu is also equal to 0. And so this equation, that by fiat, these functions will satisfy these extra constraints, which is that this shadow source term also appears to be covariantly conserved. And that puts specific constraints on the off-diagonal components and the diagonal components. Notice when the p's, the off-diagonal pieces, are 0, we say that h is simply a function of space and not time, which is similar to the electromagnetic example. Okay, fine. You have these source terms. You can simply ask, what do these source terms do physically? What do we expect? The simplest version is where the off-diagonal terms are 0, and we simply turn on the 0, 0 component. This is now some arbitrary function of space. And so I have some extra term here. And now if I have this extra term in my shadow t mu nu, I can rewrite this in a tensor invariant form. If I have a u mu and some function rho, I can write a shadow t mu nu, which is rho u mu u nu. Of course, this just looks like a pressureless dust. So this is where we say this sort of looks like a source term which could act as dark matter. To show that this is dust, and actually this is generic dust, we can do some calculation which cannot be followed during a talk, but I'm going to do it anyway, very quick. 3 minutes of napping. There's a t mu nu of regular dust. If I have regular dust in the synchronous gauge is where I assign coordinates to every point of dust. Then in synchronous gauge, you would find that many of the Christoffel symbols vanish. And so when I compute d mu t mu nu of regular dust, so I multiply it by square root of minus g, I'll get 3 terms. And this will simplify because u is in the time direction and because of vanishing of various Christoffel symbols. And using an identity, which is that the derivative, or d mu of square root of minus g, is equal to the Christoffel symbol times square root of minus g with contracted indices. I can remove this Christoffel symbol and get a nice simple equation, which is just that u nu times the time derivative of rho square root of minus g is equal to 0. Or in other words, rho times the square root of minus g for generic dust in this gauge is of the form a function of space divided by square root of minus g. So these source terms are simply the most generic version of a zero velocity dust as initial condition in synchronous gauge. You can ask perturbatively how this acts. Well, it's going to act like a pressureless dust. If you take this h of x positive everywhere, then you can do a remaining coordinate redefinition to turn this into a constant and absorb that spatial dependence into the square root of minus g. So now literally this is just a constant over square root of minus g. That's your dust term. At linear order, then you can expand what this dust should look like. And at linear order with this metric, you find that the dust contribution goes as this small perturbative part of the metric over 2, or that the perturbations in the matter dot is equal to minus h dot over 2, which is the standard expansion in linear perturbation theory and cosmology. If you say that, yes, it's a small perturbation around h, but you add or allow yourself to add small perturbations around the off-diagonal terms around 0, then because of these constraints, you can see at linear order that the time derivative of a squared times delta p is equal to 0. That means delta p goes as 1 over a squared, and the term that appears in Einstein's equations, delta p over square root of minus g, goes as a to the minus 5. That means if you start with some conditions like this, small perturbations around homogeneity and isotropy, then actually the off-diagonal terms redshift fast and redshift outside the horizon. So this quick redshifting would give an argument for why we would only get the first term. However, the smaller the structures that form in the early universe should then naively have a larger version of these off-diagonal terms. And so at very small structures, there may be something non-dust-like that appears. The generic form of this shadow matter requires a new vector. So if we introduce a new spatial vector, q mu, you can rewrite the full t mu nu in terms of this dust term, and then these off-diagonal terms. These terms are called a heat flux. They do not behave as pressure, but they do leak density from high density regions to low density regions, for example. You could also do crazy things, which is that you could introduce a source term that could be negative in some places. And if it were there, because there's no short distance physics associated with it, it doesn't have short distance instabilities, but it would mimic the existence of negative mass particles in the universe. If H was negative everywhere, or if H was positive everywhere, but there were these off-diagonal terms, because they blue shift much faster in the early universe, at some point they should take over, and those terms would cause NEC violation. Again, without short distance instabilities. One could imagine then building solutions where you have, say, a bouncing universe, albeit very inhomogeneous, or possibly building wormholes locally in the universe. Now, the reason I brought up the E&M example was that it's a toy example that we understand. And what's interesting about, well, what's not interesting about E&M is that we could never tell the difference between this source term and some decoupled charged particles. Here, if we now add gravity, we don't want infinite mass charged particles. So we put in our source terms and ask how do they behave with the background of gravity. And what we find is that that shadow charge, that background charge, then also redshifts in precisely the same way as a gas of massive particles, as 1 over a cubed. And the shadow charge density then can be simply written in synchronous gauge in the same way. So what this looks like is there should be a component of dark matter which is actually charged, but not made of particles, made of, say, continuous charge densities. The purpose of this slide is to show off something I realized in the calculation, which is not understandable in a talk, but I have beautiful symbols that I've added, so I wanted that to be part of the talk. If you add GR and E&M and you add the source term for charge, you discover that even though the source term of charge is not a real particle, the electric fields they produce are real, and they do appear in the real T mu nu. And so you have to add additional source terms to the gravity part in order for the full shadow and matter T mu nus to be covariantly conserved. And so that modifies the constraints.
So
Yeah.
are you telling us that this way of quantizing theory can actually be distinguished from conventional quantization with background either charge or matter or charged matter?
Yeah, so the basic charge in the electromagnetic case, you can't tell the difference.
Okay.
But you can send the mass to infinity to do that. Or really, you're sending the kinetic term to zero for those fields. In the case of gravity, the 0-0 component, again, there's a decoupling limit where you could add particles and turn off all couplings whatsoever. You can even say fine tune away quartet couplings that are generated by loops of gravitons. So there is a decoupling limit for that as well.
Okay.
What I'm saying is that if you add those off diagonal terms in gravity, the full set, or you do the Gauss's law piece in the case of a background gravitational field, I don't know any normal field theories where the decoupling limit can give you this, where the short distance physics is sane.
Okay.
So yeah, in some sense, who cares about all this? It's only interesting if it generates phenomenology that you couldn't get in a normal field theory, and that's what we're suggesting. So we found that if you loosen the constraints on GR, starting from a quantum theory of GR, last slide. This could explain why we think there's some matter in the universe that we can't couple to except gravitationally. The new source terms for electromagnetism would then generically produce a charge component of this fake dark matter. It could affect the CMB, galactic dynamics, or BBN, or give some sort of direct detection. It's going to be screened by the standard model plasma. It's going to be complicated physics. And we're thinking about those sort of detection ideas. But the new source terms could also do crazier things that could violate NEC and allow us to produce phenomena that otherwise wouldn't be necessarily possible without microscopic instabilities. And if shadow matter is most or all the dark matter, it's in conflict with inflation, because it is just a source term as an initial condition, which means it redshifts the way you might naively think any of these things redshift. And so if there's inflation in the beginning of the universe, it solves the monopole problem that is all possible initial functions for electromagnetic longitudinal modes and the gravitational non-dynamical fields. If you like it for dark matter, then one needs a different sort of initial condition other than inflation. And since there are 10,000 or so papers on inflation, it may be worth thinking about something else. Okay, that's it. Thank you.
Questions? Comments? So there's no way to reproduce this after inflation?
No. I mean, we haven't found a way. It really is an initial condition, and
People
inflation.
talk about monopoles being reproduced after inflation.
They're, yeah, in that sense, they're dynamical, right?
Right.
Because you could have a UV story where you can still now relax the fields in principle into monopole states. Here I don't see it. Here you really, these really are just, you're turning on parts of the electromagnetic field or the gravitational field, which are non-dynamical. There's longitudinal parts. Like saying an electron gives you an electric field. Now I'm allowing, don't put the electron there or blob of charge, just put the longitudinal field.
And there's nothing dynamical that can turn them on after inflation.
Right, they're not, yeah, they're not dynamical. Which is why this is not something that gives the photon a mass. It's not, you're not going to get an index of refraction for the photon, but you can't wiggle anything. So there's really nothing that turns them on. And therefore it's a super selection sector in the same way that once you've started, you're stuck with whatever that is. And inflation just reduces the magnitude of everything.
So sorry if you said it already, but would the shadow dark matter have any different observable consequences to regular dark matter, or does it behave just like lambda CDM?
Yeah, no, the general version of this story has off diagonal terms, and these terms, if you're around something perturbative, I mean, if those terms are small, they redshift fast, but the But you could start from initial conditions where the smaller structures have those terms. And those terms, they do something funny. They actually, the divergence of those off-diagonal terms, they contribute to the source term, which is matter. And so you can have dynamics where those extra terms cause densities to flow within a nonlinear structure, which will be different than just basic Maxwell-Boltzmann like distributions. So in principle, one should solve distributions where you add those terms, and they would appear. And so the smaller structures may be more interesting in a generic naive example than large structures, or maybe small structures within galaxies if structure formation was made by a lot of small things creating a large thing, and then depending on the dynamics, it could live inside of galaxies also.
Any other questions? Not, let's thank David. Oh, there.
Just a very quick question.
Yeah.
So in many regards, it's like an effective theory of actual dark matter and even maybe charged black holes where they're so heavy that the charges just sort of follow geodesics rather than respond to electric fields. So you could say in that sense, it's sort of got a, it's like an effective theory coarse graining over dark matter.
That's right.
But it has funky phases, like you could have negative mass and things
Yeah.
like that, where we don't have a microscopic thing. The fixing it with synchronous, so the temporal gauge for electromagnetism is a very nice gauge. It always is, it can apply everywhere at all times.
Yeah.
Synchronous gauge in gravity, my understanding is these gauge fixings are like you can use them at some time and things won't go bad for a while, but eventually coordinate singularities sort of kick in and so on. In a sense, here they've become physical. They've come to life in the form of the dark matter. Normally, therefore, any sort of coordinate singularities you would get in a true theory of real dark matter would be ironed out in the UV by the fact that it's really dark matter, it's a bunch of particles, et cetera, et cetera. Here, you don't have that option, right? You've just got this sort of, so my question is, are there kind of coordinate singularity crises in this theory that sort of force you to try and say, no, replace it with dark matter?
Right. We believe there are not. And the naive, so what steps do you take to get to this classical limit? You decide that you're in some coherent states, the classical states of those operators. And then, so let's just allow ourselves to start from the classical limit first and add these to our source terms in synchronous gauge. So around some time slice, to arbitrary accuracy, you can do a gauge transformation to go to Newtonian gauge or Poisson gauge, something that's okay at all orders, a well-defined gauge transformation. If you do that, then you simply evolve, you lose those coordinate singularities that are coming in the future. So what are those coordinate singularities? In synchronous gauge, it's you assign coordinates to two different bits of dark matter, and at some point those geodesics cross. Right? So that is a true coordinate singularity, and also not a true singularity. If you allow the density of the matter to be finite at all scales, then there is no physical singularity that occurs in that crossing. And you see it because you can reparameterize everything classically. And you also see it in simulations where people build simulations with 100 solar mass dark matter particles, or 20 solar mass dark matter, and they look to see if that short distance physics ever matters on the structure of the large scale, and it does not. And I think there are some famous papers that show that small scale physics exponentially decouple from large scale physics. I can't remember, Criminelli, that thing. So everything I said is classical, and which is to say that I could say every gravity is classical, and I'm going to add these source terms and see what happens. Nothing bad happens. And then you can ask, is that basis of coherent states, which is effectively what I changed when I did my coordinate transformation, sensitive to the UV of the Hamiltonian theory? And I believe it is not. I don't have a rigorous proof, but I believe it is not sensitive to UV physics of the Hamiltonian theory. The sets of states don't care about the UV physics. I do think it matters at the horizon of a black hole. And I think that transformation is something that really requires some violent redefinition of coordinates in space and time. And then it is sensitive to arbitrarily high energy physics. And so if your theory is not Lorentz invariant, doesn't have the full symmetries up to arbitrarily high energies, you would ask, does it make sense to think that the horizon of a black hole is empty, that follows you or not? So that, I think that's the problem that lives in this. If you started this whole story in a different gauge, you can get different effects. And in fact, there is a sort of cockamamie, so like Coulomb gauge, you set A0 equal to the integral of J0 over x minus x prime. A0 becomes an operator that depends on the matter. So you can set a gauge like that in the gravitational case for the homogeneous modes, and you can get unimodular gravity. So you can get that the source term is not dark matter, but redshifts doesn't redshift. And so so this is not a prediction of all possible ways to quantize. This is just this class, and I find it the simplest class.
Okay, let's thank David again. Not only David, David Shih, who's going to also tell us about dark matter and machine learning and the rest of the type.
Okay, well, let me thank the organizers for the invitation to come back to Minnesota for this wonderful workshop. I should start by saying I'm running on fumes. My flight was delayed like 6 hours last night, so I got in at 3 a.m. So these Newark delays, they're a real thing. Yeah, okay, but I'll do my best. And I also was looking over the programs, and I think I might be an outlier in this talk. In this conference. Maybe I'm the only one talking about machine learning, anything, or anything even with data analysis. So if I'm wrong, you can raise your hand and self-identify. But anyway, so I thought, what should I do to give this talk? I could either give like an overview, which might be a bit heavy on the hype, or I could really drill down on one specific project that I'm especially excited about. But I decided to go with the second option and tell you about this work that we're doing, which is sort of a new way powered by modern machine learning to see the dark matter around us using this exquisite data from the Gaia Space Telescope. So that's what I'll talk about today, and I hope, what are the benefits for this talk, given the audience? I hope maybe 2, 3 of you will leave the audience feeling like, oh, maybe leave this talk feeling like, oh, maybe there's something here that's interesting, and maybe I could someday see myself working on it. For the rest of you, I guess sit back and enjoy the pretty pictures. Okay, so good. And before I start, I should thank my awesome collaborators. Sungwoo, who is recently at Rutgers, is now in Korea. Eric is a student of Matt's, working closely with me on this project, and will be on the market in the fall. So if you were one of the 2 or 3 people I hope to interest in this kind of stuff, take a strong look at Eric. He's really amazing, and he's driving this work forward. Okay, So the context for today's talk is dark matter from local dynamics. So looking at the dynamics of stars, primarily in our Milky Way galaxy, still remains one of the best astrophysical probes of dark matter that we have. It's by looking at such things that we know we have some idea of how much dark matter is around us, which is an important input to direct detection experiments. And any handles we have on the dark matter profile and substructure is potentially sensitive to what the dark matter is and is a complementary probe to actually direct or indirect detection. So yeah, so the Milky Way is a fascinating dark matter laboratory. And so the general idea for many decades now to probe dark matter using stellar tracers is, using basically their kinematics in one of two ways. So one classic way is rotation curves. We all know this is one of the early evidences for dark matter. And so we can do this in our own galaxy. We can look at circular orbits of disk stars and measure the gravitational potential or the enclosed mass with assumptions on spherical symmetry of the system. The other way, which is almost as old or equally distinguished way of detecting the dark matter, is using statistical properties of tracer stars. So rather than look at individual ones that are following specific circular orbits, we can look at the distribution of a collection of stars under some assumptions of equilibrium. Usually, we can study their distribution and infer what potential is giving rise to this equilibrium distribution, which is coming from the dark matter. Okay, so that'll be the setting for today's talk, is looking at statistical properties of tracer stars. And the hero of the story is really the collisionless Boltzmann equation, which you see here. So this is an equation for the stellar phase space density, shown here. So this is f of x comma v. And in general, the stellar tracers should obey this collisionless Boltzmann equation. And the important thing is that the last term here contains the acceleration field. So the accelerations that the stars experience in response to the gravitational potential. Good, so stars are well described by the collisionless Boltzmann equation. And if you look at the right kind of stars, at least, they should mostly be in dynamical equilibrium. They've been around long enough, and the Milky Way has been quiet enough that they've settled down into an equilibrium state. In that case, the phase space density is constant in time, and the collisionless Boltzmann equation gets replaced with the equilibrium collisionless Boltzmann equation. So we get rid of all the time derivatives, and we're just left with these two terms. Okay, so if we know, so basically the idea of using stars and their distributions to infer about the galactic potential is if you know F and you know V, you can use this one equation to infer what A is, and then you've learned something about the potential. So what I'm going to talk about today is a new approach to do this, using some techniques from modern machine learning and the unprecedented coverage that we have from Gaia data, which, by the way, being astro data, is downloadable, open, so anybody can take this data and play with it. So that's what I find so exciting about this. It's not like the LHC where we're forced to just live on the outside and come up with crazy ideas that maybe the experimentalists will pick up. So here we can actually go and do stuff. So the approach that we developed is one where we can directly solve this equilibrium CVE and learn the galactic acceleration field in a way that's data-driven, model-free, so non-parametric, doesn't assume anything about symmetries, and also doesn't bin the data in any way. It's fully different. And of course, from these accelerations, we can infer also what the underlying potential is. And if we take another derivative of the accelerations, we can also infer what the mass density is. Okay, so good. So there's sort of two steps to this process. So that in the first step, we fit something called a normalizing flow to the Gaia data. So this is where the miracle of modern machine learning comes in. And this is the only place that I'll be going into detail about anything machine learning related. So, so this is the tool that we're using. It's a powerful class of density estimators that are also generative models. If none of those words make any sense to you, let me explain. So what these sort of ML algorithms can do is they can take some data represented here, sampled from some unknown distribution that we want to learn about, and they can fit basically a function to learn that distribution. And they do this in a way which also enables you to generate more samples from the same distribution. Okay, so what's happening in this diagram is what you're constructing is basically an invertible map between a tractable, like a simple distribution that you can sample from, like a multivariate Gaussian unit normal distribution. And this is an invertible map from here to the data. And if you can construct such an invertible map, then you go this way from the data back to the this is called the latent space. Then you estimate the probability density through this change of variables formula. And if you go this way, sample from the unit normal, and you transform it into data, then you're generating more samples that look like the data. Okay, and the nice thing about these models is that they're very straightforward to train. They're very straightforward to fit to the data using the likelihood function, basically, that you're learning from the data. You can train these models with the maximum likelihood objective. And so one of these transformations is usually not expressive enough, and so what you are allowed to do is basically, because they're invertible, you can chain together as many of these as you want to get a sort of an arbitrarily expressive transformation from your latent space to your data space. And that's where the flow comes in the name, is you imagine flowing from the data back to the normal distribution. That's why they're called normalizing flows.
So David, what happened to the inexplicit parameter theta between the previous one?
Good. So theta here is what we're fitting to the data. So yeah, I didn't, you mean in this slide? Yeah, I didn't indicate all the thetas, but each of these F's would have parameters associated with them. And this whole thing would have I just didn't write the theta there. Yeah, thanks.
But some hidden parameters of my sample. Some
Yeah, so these are the parameters of the neural network. So there might be like 10 million of these that we're going to fit to the data or something. Yeah, so that's where this thing gets its expressive power. Yeah, good. So here's just an animated GIF showing you a transformation from a two-dimensional Gaussian distribution to this. It's called the two moons distribution. It's sort of like a benchmark case for all these density estimating generative model approaches. It's so showing you how we can basically get from two-dimensional Gaussian to this two moons distribution through a series of what are actually linear transformations. So this will be a normalizing flow with, I think, 3 discrete steps, and it's invertible, so you can run the GIF forward or backwards, and points sampled from the two-dimensional Gaussian are mapped to points sampled from this two moons.
Is this a phase space or what are the coordinates?
This is toy data.
But what are the axes supposed to represent?
Nothing, just toy data. Yeah. They're supposed to represent like the cream filling in a Swiss roll. Well, this is just a totally abstract toy example. Yeah. Good. Maybe what you were asking is in our example that we're going to do with Gaia data, this will be phase space. So
that's what I was.
Thanks. Yeah. Sorry. Sleep deprivation. So this will be a 6-dimensional phase space in our example. Good. Okay. So in the light of time, maybe I'll skip the details. So we use a particular implementation of normalizing flows. So this is what sort of comes to us from the machine learning world, and but we're sort of developing, I think, interesting ways to use these techniques for our physics problems. Okay, so the other crucial ingredient to our project is the Gaia data. So for those of you who haven't heard about the Gaia Space Telescope, This was launched in 2013. It recently ended. It ran out of thruster fuel or something. So currently we're on data release 3, and I believe there's plans to release up to data release 5, but not for several years at least. And so what this telescope is doing is it's scanning the sky and producing the most complete ever catalog of Milky Way stars ever produced. And so that amounts to about 1 billion stars out of 100 billion or so that the space telescope has surveyed. And what it can tell us is the angular positions, the proper motions, so the motion on the sky, the color and the magnitude of these 1 billion stars that it's seen. And for a much smaller subset closer to us, it can also tell us about the distance and the radial velocity of these stars. So for a smaller subset of nearby stars, Gaia gives us the full 6D phase space. And that's the key ingredient. So if you look at the stars that have 6D kinematics, there are about 35 million of them, and they're located within 4 kiloparsec ball around us. And for this analysis, we'd like to take a subset of these stars that is complete and unbiased. So there's this famous bias in astronomy, which sounds totally obvious, but it gets a name, Malmquist bias, which is that, farther things are harder to see. So you're biased towards brighter things the farther out you look. So we need to correct or account for this bias. And we do this in a standard way in astronomy. So Gaia tells us that it's complete up to some observed magnitude. And so to create an unbiased subset, we require all the stars in our data set to be bright enough that they could have been seen anywhere in our volume. Okay, so that basically puts a threshold on the magnitude of these stars and results in 6 million stars. That's what we ultimately analyze. Here's their color and their magnitude shown here. And this bright overdensity here, this is called the red clump. These are old red giant stars, believed because they're very old to be in equilibrium, and they've already been widely used in other analyses that aim to measure the dark matter potential using stellar tracers. So this is a well-established, basically data set that we're reconstructing ourselves from the Gaia data. Okay. So here are some initial results. We have fit the normalizing flows to the phase space of these 6 million stars. So this is the actual data shown as a 2-dimensional histogram in various slices. These are galactic coordinates. So B is going off the disk, L equals 0 is going towards the galactic center, and L 180 is going away from the galactic center. And so of course the 2-dimensional histograms are a bit blotchy. And then the normalizing flow that we learned is supposed to resemble these, including all the dark spots that I'll talk about in a moment, but of course it's smoothed out. Okay, so here's another look at the same data, but at 1-dimensional slices. So in X, Y, Z, galactic coordinates, the galactocentric coordinates, and velocities, showing that we match, at least in the 1-dimensional marginals, we match the data over like 6 orders of magnitude. So these are very, very good fits to the data. Okay. So having learned the phase space density, the next step is to fit for these accelerations. So going back to the collisionless-Boltzmann equation, you might wonder, how do we do this? Because this looks like it's just one scalar equation for 3 acceleration components. So is this an underdetermined system? So actually the answer is no, because you realize that the acceleration depends only on the position, but the equation here also involves velocity. So there's actually infinitely many equations, one for each choice of the velocity, that are all constraining simultaneously the same acceleration in that position. So we can overlap all these, so it's actually a very overdetermined system, and we can overlap all these simultaneous constraints to get sort of a best fit solution for A at every position X. So we just construct the simplest possible constraint, like a chi-squared basically, or mean squared error loss, that lets us sum over all the velocities that are given X, and then solve for this A of X. Okay, and then the last problem we have to confront is the problem of dust. So as you saw on the previous slide, there's all these blotches in the data, and these are real things. So out there between the stars are sort of cold, literally dust, grains of dirt and stuff. So this is a very interesting subject for study for astronomers. For us, it's sort of a nuisance, and we have to get rid of it because stars behind the dust you can't see as well or at all, and so this affects the completeness of our data set and prevents us from doing the collisionless-Boltzmann equation. So here we actually had, I think, a pretty nice solution to this problem. So we figured out that you could actually simultaneously determine the phase space density, sorry, the accelerations, and what we call a dust efficiency function. So it's how much stars are blocked or lost by dust located along the line of sight of X. And the key point is that this dust efficiency doesn't depend on the star's velocity, just its position. So if you plug this in to the CBE actually becomes this. So in terms of the observed phase space density and this dust efficiency function.
Dave?
Yes.
So that's important because the mass of the individual stars are important. I mean, you have some cutoff so that things are bright enough.
Yeah.
Presumably, even with dust, you'll see.
Oh no. So yeah, the completeness of Gaia, I guess, doesn't. Let's see, what's the right way to say it? I guess the dust. So our cut was too simplistic. It only takes into account this Malmquist effect distance, and the dust is on top of that. So yeah, that affects the observed magnitude of the stars significantly. Yeah, so that's why we have to account for this. And yeah, so the key point here is that the velocity dependence of these two terms, the acceleration term and the dust term, is different. So we actually still have an overdetermined system, and we can actually simultaneously determine both the galactic potential and the dust efficiency function with the same data. So we actually get both of these then sort of for free. So this is our new sort of loss that we're trying to minimize. And we just parameterize both the dust efficiency function and the potential with simple feed-forward neural networks. And then we get both as solutions to this over-constrained system. Okay. Excuse me. So here are some pretty pictures now showing how we correct the phase space density. So here's the actual data with all the dust clouds. And this is our learned phase space density, the normalizing flow, which also sees the same dust clouds. These are all the stars up to 3.5, or no, sorry, I think in a shell of 3.5 kiloparsecs away from us. And so this is our learned dust efficiency function, which tracks very well where these blotches are. So we learned this all from the data and just assuming equilibrium CBE. And so after we correct for that, this is the corrected number density, which looks very smooth. So it's really working. And we could do this sort of at any distance. These are the very nearby stars, half a kiloparsec away. There's still a little bit of effective dust that's well corrected for. And stepping further out, so just keep an eye on this final thing. It's smooth, sort of no matter what distance we're looking at. Okay.
Dave, one more question.
Yeah.
So is this useful for CMB people? As terms of subtraction, have you learned enough?
So I think, well, the dust field, this dust efficiency map could be useful for that. But this is very specific to stellar astronomy. It's telling us which stars are blocked by the dust. But it's possible that this could be converted to something useful for the CMB.
It's another template. It's only the inner 4 kiloparsecs,
Also,
2.5,
yeah.
but it's, I don't know, it's
it tells us
consistency
something about,
maybe.
certainly tells us something about where the dust is. And so, yeah, so that this is very different than the way astronomers normally talk about dust maps. They like to talk about extinction and reddening coefficients. So yeah, so that's something on our list of things we'd like to do is to cross-correlate this more with the astronomers. Good. So in my remaining few minutes, let me just show you some results. So these are all preliminary. The dust part of our project is out, and all of these results are not out yet, but hopefully soon. So here are some comparisons of the potential, galactic potential, with a sort of benchmark Milky Way potential from one of these astro packages called Gaia. And so the dashed lines are the Gaia version of the Milky Way potential. So this is some simple parametric potential that has been fit to a bunch of different data sets. And this solid line is what we're learning directly from the Gaia data, and they match pretty well, I would say. And they even match in the highly dust obscured disk. So our dust corrections really seems to be working. These are now the accelerations, so one derivative of the potential, again compared against Milky Way potential as a reference. And this is, for instance, the acceleration in the z direction as a function of distance off the disk. So as you go off the disk, the stars are actually experiencing a gravitational force pulling them into the disk. So that's what's shown here. And again, it matches quite well the sort of reference potential from other people's bits. We can also now access accelerations directly in the disk. So if you didn't account for the dust, this is what the dashed line is what you would have found. This was in a previous paper of ours. And so basically the acceleration components in the azimuthal direction and in the z direction in the disk should all be zero. But if you don't account for the dust, you find this answer, which is clearly wrong. After you correct for the dust, it's pretty consistent with zero. And the only non-zero component is the radial component in the disk. So these stars are mostly just orbiting with circular orbits in the disk, and that's what we find. The dot here is actually a measurement done by Gaia collaboration itself, so like an official measurement of the acceleration just at the solar location using distant quasars, actually as an interesting technique that they developed. So a completely different method. And so we also find excellent agreement with this measurement from Gaia. Okay, we can also compare the accelerations against other measurements of galactic accelerations that have been done recently using binary pulsars in these works here. And here they can only tell us about the line of sight acceleration of these pulsars. So we have the full three-dimensional acceleration vector, but if we just look at our line of sight, so we agreed pretty well for about 3/4 of the pulsars that they looked at. These are the poles showing you, I guess, where things are more discrepant, ordered in the size of the poles. So down here, about 1/4 of the pulsar measurements showed significant discrepancies with us. And so if this is a real thing, this could be a novel probe of disequilibrium in the Milky Way, since they don't assume anything about equilibrium, but we do. So maybe their answer is correct, our answer is incorrect, and the difference is somehow telling us something about disequilibrium effects in the Milky Way. Okay, finally, the thing you probably are waiting for is a plot of the mass density. So taking another derivative, we get the mass density. And here it becomes increasingly hard to control numerical stability. But this is what we could do in our 4 kiloparsec ball if we sort of look at shells of basically imagine shells with constant spherical radius sort of relative to the center of the galaxy. So the dark matter is spherically symmetric. Like all these points should just be functions of the distance off the disk. So that's what's being plotted here, is the distance off the disk. And you see this flat part here and a sharp rise. So this is all due to the disk, the baryon, the stars and the gas, basically. And when you subtract that out, that's known very well from other measurements. When you subtract that out, you get this mess. But this mess is very noisy, but it fits well, basically something flat, which is the dark matter density at the solar radius. So that we get a number which is very consistent with other measurements, 0.4 in our particle physics units, with pretty good error bars. And I would argue more realistic error bars in that we don't assume a very restricted functional form for our fits. So yeah, so that's one of the main results. And something that we're working on now is using this measured mass density of all of these points, basically, plus the ones in other spherical radii, using all these points to fit parametric potentials. So now at the very end, we can inject some parametric potential and see what inference we can get from that. So we're doing fits, for instance, to the NFW potential that look like this. We're also exploring generalized NFW, other dark matter potentials, see if there's any preference. This is one that I think is perhaps most exciting right now, is we can also constrain a dark disk, which maybe in case you were still interested in dark disks, these are the previous limits from other methods. And we're able to improve on those limits by up to 2 orders of magnitude for a very thin dark disk.
Dave,
Yes.
on the previous slide, the error bar, is that pure statistical?
Ah, good. Thanks. Yeah. So so the errors we try to quantify in a variety of ways, but basically we try to take into account the measurement uncertainty from Gaia that they report, the finite statistics of the sample, which we get from bootstrapping, and the randomness. You get a different answer every time you train these neural networks because the training itself has a randomness. So we try to quantify all three sort of simultaneously, and that's what all these are meant to do. Yeah, thanks. Okay, so let me just start with a summary. I think hopefully at least one of you is interested in this. And we've developed a new technique to simultaneously infer all these different things in a 4 kiloparsec ball around the sun using this amazing data that we have and the powerful new machine learning techniques. Unlike previous approaches, our method assumes much less about the model. And so these are some of the other things that we're thinking about. So in the interest of time, I think I should probably stop.
I had actually similar questions that David had. But I'm not sure that you answered what I was asking. Or might have answered what he asked. The error bar, I think, was on the local density, or 0.4 plus or minus 0.03. That's what's very small. I don't know. I can't comprehend all of the error bars you have there, but the one at the top I do understand.
Good, yeah.
And that one's very small. So how confident are you in that error bar?
So that error bar is from basically fitting, after we do the subtraction, we fit basically a spherically symmetric answer. So in this data shown here, basically a flat line, so constant, we fit a constant to all these different points after the subtraction. And that error bar is just propagated from all these error bars. So it's the error bar on that. So
That's one that's usually much larger.
no, actually, so we have a backup slide here. So this is from our published. Okay. This is from our published paper. These are the error bars from this reference from different older methods of measuring the local density. These are genes analyses. And
Yeah, but the values of the density are scattered, way more than 0.03 here.
Indeed, yeah. So that's what I'm saying is that these methods all have some significant, we believe, some significant sort of systematic bias because they're all assuming very specific forms for what they're fitting for, and maybe different forms.
Is yours up there?
So our previous measurement is shown here. So that's the blue line, which is consistent broadly with everything, and has, I would argue, a more realistic error bar because we're not restricting ourselves to like a very specific functional form for the potential.
That's critical for direct detection.
Absolutely, yeah.
But that's averaged over a few kiloparsecs.
So, right, so to be fair, this result that we get is averaged over, it's not just the dark matter here, it's assuming spherical symmetry at this point. So it's averaged over all the measurements that.
But it is the local density because
It's the density, assuming spherical symmetry at the solar radius, so 8 kiloparsecs, but anywhere in an 8 kiloparsec ball, yeah.
Hi, thanks for the good talk. As someone who's probably least likely to engage in machine learning, unfortunately, but let me ask you this. If you had a component of dark matter, let's say the dominant dark matter, which was something like fuzzy dark matter, which actually has inherent time dependence in its energy density. If you had the timestamp on data points you have, is there a way to extract that there's actually some sort of sloshing or oscillation?
Yeah, in theory, we could repeat this analysis for each time slice guide. Currently, they don't provide that level of detail. They have internally basically astrometric measurements of the stars at each time slice that they observe it. That's how they're able to get the velocities. there's basically not enough precision, even asymptotically, I think, to resolve the accelerations directly star by star. But potentially, if you look at many stars together, you could try to see something time dependent. Yeah, so I think they're talking about releasing that kind of information with the next data release, DR4, which they say is sometime in 2026. So that's going to be a very exciting new opportunity, potentially. Yeah.
No, I missed how you were dealing with the equilibrium assumption exactly. Are you restricting to only stars that you think are old, or are you weighting them more? Or and how much difference does it make?
Good. So let's see. Well, okay, yeah. So we are doing a cut that ensures completeness and unbiased. So this is and then what we're finding empirically that this cut also is really dominated like 70% or so by this red clump, which is believed or known to be well described by equilibrium distribution. So it sort of just works out for us that the cut we need for completeness is also the cut we need to sort of highlight the equilibrium subpopulation. Yeah, so that's all we're doing. We have explored, I can find this, yeah, we have explored ways of, here it is. So we have explored ways of even cutting tighter on this red clump, but those all have seemed to bias our fits significantly. So we ended up just going with this flat cut and hoping for the best, basically. Yeah, but it's possible that with a better technique, we could make things even more in equilibrium with a better selection of the stars.
But you had sort of have a bound on how much difference it might make. Sort of.
Yeah, so I don't have the plot, but we have ways of detecting basically, so this is one thing in my outlook. So if you go back to the actual CVE that has the DFDT per minute. So we're able to we assume this is 0. We do this constraint for many different velocities at a given position. So we're able to actually get a distribution of, so the constraint is not perfectly satisfied for each velocity. So we're able to get a distribution of this, like the non-closure, at a given position. And so we think that could be an interesting probe of DFDT. So of course, the mean is always going to be set to 0 by our fitting, but maybe the standard deviation or something could be a probe. So maybe places X where the spread is bigger are places where there's more disequilibrium in the data. So these are things that we'd like to explore further.
Okay, well, I suggest maybe that we thank David again and the inefficiency of your chairman. We're running late, obviously. The first coffee break, which is probably the most important one. Let's meet again at 1:45. So a little bit shorter break.
Yeah. You know, I'm very fun. You might be the first one.
Being happy, the Shih.
Sorry, didn't I just say?
Yeah.
If you talk about the maps, you can write the whole thing in this map. The only difference is the manifold contains symmetry research. If you put this point, the Riemann tensor has like some big simplifications. They can allow you to derive like sort of all orders relationships. Yeah, so, that's what we're working on. And so we were able to get these relationships and now we're kind of trying to like match it onto like sort of traditional calculations to show we get the same thing, like one line of algebra. instead of a bunch of lines.
Yeah.
Yeah,
Oh, cool.
yeah, anyway, hopefully it comes together in time, otherwise I'll talk about it.
They in a situation where I go talk, I want to mention something in progress and, still waiting to see if I can leverage this. Gotta find a way to-
Yeah, it's a phrase, it's so shocking, it's progress, it's good feedback. So I like it, but, it's also like stressful.
No, not yet. Nice.
Okay, let's start the second presentation. So the first.
You explain my
Pomarol.
All right, I'll move on.
Okay, thank you very much. It's a pleasure to be here and now I'll be talking what I've been thinking in the last year, that is to understand a little bit better the strongly coupled theories with these new methods, the new method that appear with the bootstrap techniques. Okay, and in particular here I want to discuss a little bit when you couple these theories to gravity and what information can get out of it. Okay. I mean, the motivation for strongly coupled theories is obvious because I mean, you see the title here of the conference. There are many of you doing the matter of actions, inflation, or even composite heat that are really down in the last option, but with Rana looks like going up a little bit. Okay, there is interest on addressing these problems with strongly coupled theories. Okay, and of course, when we talk about the strongly coupled theories, we have to face the problem that it's very difficult to make predictions. Okay, so any analytical approach is very welcome. Okay, most of the cases we do effective field theories. That works very well, depending what you're asking. Holography was, of course, very important, and we heard a bit from Raman also that allows to give predictions. And but I'm more interested is in these techniques that are called bootstrap that correspond to demanding good properties to the amplitudes. Okay, Lorentz, positivity, and locality, as I will more or less review later on. And I think are very good. Okay, in fact, it indeed allows you to fly. Okay, and get a lot of information that you would not have expected. The first analysis we were doing, and also the group in the study group, Rastelli's group, was by bootstrapping amplitudes like the pions. Okay, and I will give a detail how you do this, but here I only want to put the result we were getting. Okay, when you do this, okay, even that you don't know much about what is a theory, we were assuming here theories that are described by infinite set of states, okay, like Lachen QCD. Okay, when I was able to get very strong bounds from the Wilson coefficient of effective field theory, okay, that for example, you have higher speed theory, you have to live in this blue narrow state, okay, and not only this, you see that different models where they can sit. Okay, for example, Higgs model could sit there, because of course it's not made of higher spin, but a holographic model that will live around this corner. Okay, stringy model will live here, the generic model will live here. Of course, we were aiming to look for QCD, but we couldn't find it. Okay, this why they live here, usually because they are kings in this region, allowed region, and usually in the kings you find these simple theories. Okay, so there were a lot of things that one could get like this, even comparing with the lattice data. Okay, comparing with the with people that doing lattice and trying to get similar things, we were showing that this is even better than do it all the effort by the lattice. Okay, as soon as you want to count these Wilson coefficients. You can also learn about the qualitative feature, like what the couplings of this resonance to pions, was dominated by the lowest spin, in a very efficient way. As soon as you increase the spin, the coupling to pions of the resonance will really decrease it going to zero very fast. And we're able to even quantify how much, how fast. So due to these approaches, we wanted to continue with this plan. What can you learn? And here, what I want to do is to see what you can get when you couple gravity to this strongly coupled sector. And we're interested in models with have a U1 gravitational anomaly, so you have some kind of eta coupled to the gravitons. Like, for example, this eta could be an axial model with the Axion, of course, or in QCD, where you have an axial gravitational anomaly and that couples to this away. So assuming that you have a light state like eta that couples to the graviton, what can you do about when you do the bootstrapping? So the idea was to bootstrap the graviton coupling amplitude. And you could see that these different effects, will come if you have this eta, of course, will come interchanging the eta. You'll have that low energy will be dominated by this eta change, due to the coefficient that related with kappa G, what we call kappa G related with the anomaly. And of course, you'd also have a change of a graviton coming from GR, or possible deformation that you could have a GR like a 3 graviton new coupling. That of course doesn't appear in a minimal GR.
I don't understand.
Sorry?
I don't understand. The eta H coupling is much larger than the graviton coupling, right? Why do you add them or whatever you do? I don't understand the idea.
Okay, the idea is that I assume I have a scalar particle, that couples to the gravitons in this way.
H is a graviton.
H is the graviton, yes, sorry.
Okay.
H is the graviton, yes.
Okay.
And now let me make it very clear also the parameterization. Each time I put graviton H, I normalize this by 1/n plan. Here two gravitons, everybody squared, and every time I put an eta, I normalize it by the decay constant part. This is just to clear.
Alex, can I ask one question?
Yes.
So often to prove a like to form an anomaly, chiral anomaly using like loop on-shell approach, then you're looking at the tension between generalized unitarity with the locality or rational time. And here, I can see that we can construct that amplitude just by the same technique as any 3-point function can be constructed once you specify helicity. And is there any characteristic feature of that answer that tells me that this is associated with any anomaly at all, rather than just saying that this is just one of the 3-point function?
Okay, you say it could be this generated, you say it could be this not related with anomalies, you saying this? It could be that it's not related with anomalies.
Okay.
Anomalies has this piece, but you could have probably, you could have probably these couplings, not clearly, depends how this thing transforms,
Right.
You say the anomaly because these transform under the Shih. This is what the defective two theory of meson is the way how you see the anomaly. In general, I don't know.
Okay.
Excuse me, probably it's not a real eta because eta is has isospin, right? And then you couple it to two gravitons.
Let me say I have only this is a U1, gravitational, not isospin, not isospin.
No, but in the real world, eta is coupled, it has a isospin or SU3
is isospin zero state. Call it eta prime,
eta prime.
Eta prime,
Mean that
Don't
it's
have so many to put primes. You don't put prime, you're right.
oh, just to understand your setup. I'm sorry.
Okay, so inside this amplitude, we will see what, of course, we can calculate from your effective field theory, plus, of course, if now you have a strong sector or a new recompletion of this amplitude, of course, you will have also this contribution from these extra states. Okay, for example, that will be what we want to prove, I call the strong sector. And put it in a, like it's coming from a exchange of resonance, but doesn't need to be here the case. It could be that they coming from loops, and these are complicated things here. In this example I'm doing here, the bounds I will get that also apply in the case of loop. Now the bootstrapping technique is based on a very simple fact that when we look at an amplitude, in this case we're thinking about the graviton scattering amplitude, and we look at the S and T, and we take a look at the S plane at T fixed, the singularities of discontinuity of the function are on the real S axis, starting from the first state of you have in your strong sector. Okay. The positive part comes from if it's exchanged by, just to get an idea, if it's exchanged by a three-level particle, will come from this case will have simple poles. Okay, although you could have branch cutters, you go to loops. Okay, associated to the channel. And the negative S will come from because S is equal to minus T minus U, will come from the fixed T will come from the possible pole that you will have in the U channel. Now, if you take this amplitude, okay, the trick is you divide by S. Okay, it can be 1, 2, 3, 4, 5. We'll see. And now you will take large enough K. You can demand or you expect this amplitude by some arguments. So K large enough, you go to 0 at when S goes to infinity. Sorry, I'm supposed to put it here. Okay. So dividing by S, when you go to large S, okay, for example, force R tells you that it will come like S squared. The amplitude divided by S squared should go to 0 when S goes to infinity. Okay, so if you take a contour along the S plane at S infinity, okay, you have this kind of special relation that tell you this amplitude divided by SK plus 1 should be 0. Okay, and it's this kind of relations that you get that you want to use to get information on the state that you have here. It is the idea of this special relation because, of course, like Shih, we all deforming just the contour, you know that this will tell me that all the discontinuities here and the singularities here will be 0. Okay, and will give me a relation. We have singularities here because we are dividing by S. Okay, so when S goes to 0, of course, we have extra singularities at S equal to 0. Okay, so this thing is telling me that the singularity at S is going to 0 that has to do with low energy physics. Okay, S goes to 0 must be related with the discontinuities due to the strong sector that you are probing. You see, okay, so there is this kind of infrared relation with the UV physics. Okay, what extra states are in your theory. Okay, this is only related with light particles, or also you could have Wilson coefficient in your effective field theory, but you can do an expansion at the small ends, and this should be related with the high energy physics or physics of the other stage you have. So here is quite simple, and it has been very, what I was telling you before, has been used in the case of ion scattering to get all these bounds that I was mentioning before. It was interesting to look at the gravity, of course, but gravity is a little bit different. Okay, the first rule you get is a very interesting one. Okay, K equal 2. Okay, and you get from the origin, you get only the graviton exchange contribute. Okay, so you have the G-Newton coupling with 1/3 due to the graviton, and on the right hand side you have the equal to, you have the sum over the discontinuities coming from the strong sector. Okay, I wrote in this way where this parenthesis is what you expect is the integral that goes from 0 to infinity. Okay, of the spectral density, of course, that is just related with imaginary parts. Continuity is related with imaginary parts. Okay, so you expect here that we have the imaginary part, and after partial wave decomposition, okay, that's where the Pinger function appears here. Okay, so integral over here is the spectral function, so from the origin to the infinity. Okay, after having done partial wave decomposition. So this knows about all the states are here, and tell me something interesting also this rule. Okay, tell me that so GR is this is GR. Okay, it is G Newton times 1/T is related with all this kind of messy thing coming from the high energy sector. Okay, and they should equalize. Okay, part of GR should be equal to all these things at the high energy. The other rule that is important is the K equals 3 relation. Okay, in this case, now you put K equals 2, K equals 3 here, you get no, you don't get anymore the gravitational exchange. Okay, you get the other pieces that I had in my here. Okay, so you get K equal 2, you get this piece. You go to K equals 3, you get these pieces here. So it tells me about what we were looking for, a contribution from the anomaly square, and times these 3 graviton coupling that we thought we also put. Okay, equal to some expression that has the same general wave here, but superficial about because K is large.
So all the dynamic information is encoded in this D coefficient. Is that how I should do this?
This is a linear function, so we know this. This is coming from the imaginary part here. I do this partial wave decomposition. Okay, so I have the Pinger function that we know what they are, as a function of cosine, times the spectral densities that these depend on the physics here.
Right. Okay.
Okay.
Yes.
Anyway, in the case that are simple poles, this is very simple. This is just the residue of the pole. So go with the coupling of the particle times the delta function. Right. To get an idea of what they are. Now, usually in the bootstrap technique, you take T0, okay, and in some sense you can use, let's say that you use the optical theorem that guarantees this part is positive. Okay, you are in the forward limit, okay, and you get something equal to positive, and you use this relation to get these positive bounds. Okay. However, of course, here you have a problem, okay, because you have 1/T, the graviton pole. And of course, it's not possible to take the T0 limit. Okay? This has been known for years, and the solution has proposed a few years ago. Okay, that why to take this limit? Okay, you better keep the relation and now integrate with mirror over this pole by integrating with some function. Okay, at integration over T. Okay, with a proper function, such that guarantees that this contribution are positive. Okay, instead of going to the forward limit, where you could guarantee that it's positive, it is possible to show that you can find functions AT that when you integrate these quantities over T, you get a positive contribution. Okay, so that relation is very important, okay, because in some sense it's telling you that every state you have in the UV contribute to, so you want to think about this. This is G Newton, this is GR. Okay, so it contributes to G Newton positively. Okay, so every particle you put could give you, if you manage to find this function, and it's possible to find it, you contribute positively to G Newton. Okay, okay, so gravity in some sense is measuring, you have to pay a price, okay, to individuation. Okay? More particles you put, this is what will give you the bound. Okay, because you start putting particles, okay, they cannot cancel here, they add up. Okay.
And so this function, what's these functions A and T? You have to
I'll
find
tell
these.
you what they are, a very simple function. Have to have some properties that you can check that when integrated over these Pinger functions are positive, or yeah. I'll show some of them, but it's easy to. Now, the same particles that appear here, the same state or the same UVPs that appear here can also appear here. But this scalar will give a small contribution. Okay, when you integrate, again, you have to smear integrating over some function, don't have to be the same. Okay, over this amplitude, scalar will give always higher contribution to the k equal to some rule than at the k equal 3. Okay, first because there are negative signs here, here always appear the positive signs. Okay, but here appear negative signs and is suppressed by higher power of the mass. Okay, so you can see that any state you have in your theory contributes here positively, and here can contribute positively or negatively, but also suppressed by the mass of the part. Okay, so that's the idea that whatever theory you have, this contribution here, okay, when you integrate over that, it would be always smaller to this contribution here, because we go to the right-hand side and we know the contribution here is smaller than the contribution in the k equal to standard. Okay? And that's the basic point of the bound. Okay. So we're saying the integration of this function over this thing that has the physics of the infrared, okay, it's talking about the anomaly and this tricoupling of gravitons, okay, integrated over the B must be smaller than this. Okay, when you find the proper A, you must integrate over it. Okay, integrating from 0 to some T max that I will mention later what could be. Okay, you will like to take it the largest possible value. Okay, we will say that cannot be done.
So
Okay, so this is the basic thing where you have a relation. Okay, I have to find this A and B, but give me a relation between an Newton or n Planck with the anomaly coefficient. Okay, F5 and also in Planck.
but this bound is sensitive to the choice of A and B function.
Eh?
Am I correct?
Sorry?
The nature of this bound is sensitive to the choice of the A and B functions.
The bound is sensitive to this thing. Oh,
But will they have any physical meaning, this A and B?
No, no.
20 minutes past.
Eh?
5 minutes to 25 minutes. So
You still have about 10 minutes,
Yeah.
right? 5 plus 5.
Okay, here it is an example of the function. You see, there's many. The bound indeed depend on this function. Okay, so there's a function that I cannot explain you why I have the shape here. Okay, that I have to do with this power, but there's not something very. No, I don't know what to see. Okay. The important thing is that when you go to the T, what could be the T max? Okay, is I have to go a little bit fast now because the T max you have to be careful because when you integrate here and your T goes above this mass, because there is a pole here. Okay, T is negative. Okay, so when T is negative, when you integrate from 0 to minus T max, okay, there's a minus important here. You have a pole here, so in the this is due to the U channel exchange. Okay, so you have to be careful that when you hit with first cannot be over the first resonance in the U channel. Okay, that are particles that fit spinfold, and easily see that are particles spinfold. Okay, so it means that the T max, the best you can do is to fix it to the first resonance, and now you get a bound that looks like this, with the 7 is really coming from this thing. So you should not probably pay attention. If I change the function, we'll change the 7. But parametrical is to me what is important. Okay, you have the mass of this speed for mesons with the times the anomaly divided by 5 should be smaller to a number times a log. And this log appears only when you do for electron gravity. Okay, and it's clear what you should do with this log. Usually you say it's an infrared singularity, you have to regularize. Probably you have to do better, but probably you have to sum over them. But the idea is that probably we will not change the number here. It will be a number order 1. That is the only thing I want to say here. Okay, so at the end of the day, that there is important thing to me is that this quantity here is bounded by a number order 1. Okay. Now, so what are the forensic implications of these simple relations? Okay. Well, it implies that any effective field theory, like an axion that couples to gravitons, has a cutoff, okay? Because cutoff, what it means that is an effective field theory of axion. You go to high energy, at some point you have to hit with the spin for mesons, okay? And the mass of this spin for meson is smaller than order 1, okay? So we call it this lambda causality, okay? It's the scale where the spin for resonance must appear. Okay, it should be something like a square root of n Planck F5 divided by the anomaly coefficient. Okay, and now you learn that this cutoff is much smaller than the Planck scale. And even if you do naive perturbation, perturbation theory to see where you lose perturbativity, you see that this scale is even larger, but this lambda causality appears below. Okay? It's kind of non-trivial bound that you have in this theory. You could not see from effective theory. Okay. That's a interesting thing. Okay. I was interested in the idea of going to Latin gauge theories, and you just do again the mass of this spin 4 state must be smaller than this simple formula. So we know if you go to think you're probing a large gauge theory, okay, you know the anomaly goes like a number of colors, number of fermions also. For time probably to mention this. And we know if pi goes like in the large chain counting goes like square root of number of colors times the mass gap of the theory. Okay, so you get a formula goes like this. So surprisingly it looks like if n goes to very large, the bound comes down. Okay, because n goes, so this goes down. Okay, so it looks like the bound that you have on causality when the spin 4 particle disappear comes down. Look like interesting because we mean that very, very large n probably you fit even your lowest meson. But of course, this is not the case because one has to be careful that the number of colors is growing, the gravitational propagator is affected. And also in this particle, we expect to have lattice theory glucose. Okay, that will come to the we modify. Remember, I'm doing the graviton, of course, I'm doing GR at the 3 level. Okay, but if I have so many particles of them, it will affect the propagator. And demanding that this is smaller than the 3 level I use. Okay, so I do simple calculation. I see that if I have my what I would call quantum gravity scale, which called quantum gravity in the sense of the scale at which I cannot trust anymore my 3 level propagator for the graviton. Okay, it's not, it doesn't go like n plan. Usually we say it's n plan. It's not n plan, but n plan divided by number of colors. Okay, if you have a theory with a number, this is already known by people doing theories with large number of species. Okay? But your cutoff really goes down. So if you rescale, if you don't write this thing as n plan, but you rewrite as a function of this quantum gravity scale, okay, you see that now the bound, okay, the bound of here doesn't go down with the number of colors, but goes up with the number of colors. You're kind of losing the bound. But it's important to mention that gas and go, you know how it goes in powers of n number of colors, because I number of colors. Okay, stop. Okay, so probably for QCD like theories looks like, oh, number of colors is large, it looks like goes up to the quantum gravity scale, so I don't learn much. But this bound is important, and this is what I wanted to say in holographic models, because holographic models is those models, okay, for example, that Raman was mentioning, where you build, okay, and let me go up here, okay, when you do holographic models, you are doing models in extra dimensions, where you only consider spin 0, 1, and 2, the states, okay, and this is already going to the theory of Malvasena, that there is a new parameter that is important, that is the G is 10 mil square number of colors, that is lambda of Kaplan. That when you take it large, okay, your spin, higher spin state goes to infinity. Okay, so there is a subclass of theories in the large chain, okay, at which you can have this gap to be very large. Okay, another question is this in accordance with the previous thing? Okay, because the causality, if I does this spin form must appear, there should go a number of colors a quarter. Okay, and what would you expect from holographic models? Okay, let me take a bottom-up approach. Okay, like Alan was mentioning, okay, has 5 dimensions, has the gravity part, has probably gauge boson. Okay, in my case, I'm assuming that I need an anomaly. Okay, a couple of eta to gravitons, so this comes from what is called the Simon curve. Okay, should be non-zero. And usually, if you look at this theory, the normal, naive way to find the cutoff, we know how to do it. Okay, you have the scales here. You say your cutoff is related with the scales that appear here in 5. The plan that is the gauge coupling of the 5-dimensional theory, and the plan is scaled in 5 dimensions. Okay, that's an naive thing you do. Okay. You say my theory is effectively the theory, this is an effective theory in 5 dimensions, I can calculate. Okay, but up to the cutoff determined by the mass parameter you put. Okay, as we know all the time. The theory, plan gravity theories, for the Now, if you do ADS correspondence, you know that this M5 goes by number of colors, and this Planck scale goes by number of colors to 2/3. And of course, the anomaly goes the number of colors. Okay, and if you put this thing, you realize that in this theory, the bound I'm putting that tell me that the spin particle spin higher than 4 should scale a number of course to the 4 that appears to be much below the other scale. So again, in this kind of theory, it appears a new scale. It is non-trivial, you would not expect it from naively thinking an effective field theory. Okay. So there's a causality bound, okay, that makes the theory not, you cannot extrapolate to so high up, okay. Okay, that's a surprising. I've been working on the mammoth terms for years. I didn't know there was a new scale that, a new cutoff scale, okay, that tells you where spin 4 states should be. That's good. Okay. Now, if you go to construction, okay, because precise construction in ADS-CFT, okay, so those that you have a dual, you find that really there's a states down here, okay. For example, if you go to these models, in these papers, there's a T3 and this T3-T7 system, okay, that is n equal to supersymmetric with an anomaly, you find really that the string scale really appears much below the this M5 and in 5. So if you go precise model, of course, with the UV, they fulfill this bound. Okay? So let me just say that there are other things, okay, that you can check in this thing. Okay, 1 minute, sorry. Just to say, for example, that if you do the same, but this that with eta, you do globals, okay, that the scales with the couple to the gravity with a different scale not number, you learn other things. Okay, for example, in the holographic models, this coupling should go to 0. Globals should not couple to gravitons. You learn also that, for example, the dilaton should not couple to 2 gravitons. Okay, so it's interesting relation because the dilaton coupling has to do with the A and C anomaly, trace anomalies. Okay, so you know that this should go to 0. You start learning that some coupling should go to 0, okay, in these models, or the 3 graviton effective coupling also should go to 0. Okay? And now you can check in these 5D models. Surprisingly, yeah, you see that these couplings go to 0. Okay, so that's an agreement. Okay, with this thing, and now you can see also bound on the anomaly, because if the anomaly grows very fast here, okay, the bound was here, you rewrite it as a function of after they put in the coefficient of the anomaly. You see that the anomaly grows very fast with the number of colors. Okay, this bound will go to 0 in the large link. The states, the mass of the states of higher spin have to go down. Okay, so kind of strange, but you're getting this information that the anomaly in holographic models cannot be very large. Because I would have expected if I put a lot of number of fermions, the anomaly coefficient grows, but yes, it grows, but you will not have, seems to be an holographic description. Okay, and okay, the game can go on with other photon, graviton, these things, but let me stop here.
I want to ask a naive question. Because NC counting usually can be seen, you don't need any dynamics, right? You draw a Feynman graph with quarks, forget about eta prime. Yes. With quarks, if you need to add gluons, you add gluons, but it doesn't matter. You consider the planar diagram, and that defines just n counting. It's general. That defines the independence, and I'm sure that your limits should be at least for independence. Your whatever predictions should be consistent with that. There is no more.
Yeah. So consistent. Okay. Consistent. In the case of non-holographic models, I show that the bound goes up. We, in some sense, in QCD, okay, I was saying before, the bound disappear. Okay, you increase the number of colors, the bound goes up. Okay, it's only probably this bound interested in this kind of holographic models, where the spin for in QCDs you have a spin 1, 2, 3, 4, all of them around the raw mass. Okay, however, in holographic model you have this gap between the lightest states, lowest spin states, spin 0, 1, 2, okay, and the other gaps. It's there when this bound is interesting. Holographic model for QCD model, this bound doesn't look like very interesting. Well, you learn something is kind of that is probably I don't know. That for example, that the blue ball coupling to graviton should be suppressed because scaled like one number of colors squared should be suppressed by the mass of the highest spin 4. Spin 4 in QCDs around spin 1, spin 2, all of them are packed around there. But the spin 4 usually is heavier than the rest, a little bit. Okay, so I don't know. This can be useful or can be put in a more. But this coincides with the expectation.
Do you have a physical intuition why spin 4 greater state must be crucial in maintaining causality?
No, this is this amplitude. It's just because in this amplitude, okay, the U channel is spin 4. No, if you do other amplitude, the U channel will be spin 2, spin 3. The reason this was good, okay, because if it's spin 1 or 2, nothing. Okay, because in the holographic model, the spin 1, 2 can be like it's spin 4. So no, it's just the amplitude they took. If you take another, you get another.
I'm wondering whether there's a prehistory to the project where you're thinking in terms of something with measure or like if this coupling was big, then you could see it in some way. Like, can you do cosmological collider physics in the tensor modes of inflation where you have heavy particle decaying into gravitons, which then change the tensor non-Gaussianities? But let me just put it to you, was there phenomenal? Is this like pure theory project, or is there a secretly was something in the back of your head?
No, argument was to understand the large chain QCD property. This is what is the argument. You know this problem, okay? Understand the better, okay? Because it looks like powerful to constrain large chain QCD. In this case of the graviton, looks like for QCD, large chain QCD, not much. Okay? So you have to go to other theories, but for holography, I found it very useful. That there is this new cutoff of appeal that you would not expect from your naive way of putting cutoffs. Okay? And that was my. I didn't think much more into probably lattice, synergic with lattice people, but it's only no, I didn't look any application for phenomenology experiments.
Okay, so let's move to the next. Okay, so the next is Graham, please. And works. So the title is New Idea, the strongly coupled dogma. Please.
Yeah, so it's a great pleasure to be here. I want to thank the organizers for letting me come and give a talk, and it's great to see any colleagues and friends here. You might think this is Oregon. This is not. This is Minnesota. And it's a state park. Teetergah.
What's the name?
It's Teetergah or Teetergah. Someone
Tedagouche.
I know.
Tedagouche.
Tedagouche.
Head of the good. It's French.
It's been originally French.
I claim that
And this is Lake Superior. Yeah, I wish one of these people were me, but unfortunately I was stuck in Denver for many hours due to thunderstorms. So I'm like David, I'm also a little bit jet lagged, shall we say, or at least still waking up. Okay, so the talk today is about new ideas in strongly coupled dark matter, and specifically what I'll talk about today is light composite dark matter and its connection to non-moving particles. So I've been having a lot of fun in the past sort of couple of years on different aspects of strongly coupled theories, model building within them, and the associated phenomenology. This has a whole series of different collaborators at different points. including some of my colleagues. Austin Bates is a student at Oregon, who's really good. Of course, many of you know David Curtin and others. Puya Asadi is a postdoc at Oregon, now at UC Santa Cruz. Chester Mantle was undergrad when we did this work, and he's now a student at Harvard. Austin appears here. This work you'll hear about today, and some other work in progress. The common theme in all of this is sort of examining different aspects of what kind of theories, what kind of strongly coupled theories we might have that lead to sort of composite dark matter, and what are the associated signals from it. And what's sort of surprising to me is that we've discovered a whole number of new aspects of this, sort of new symmetries, places where the direct detection rates are much smaller than you might otherwise expect, places where the spectrum includes a diverse set of states, not just states that look sort of WIMP-like, but also singlets that mix in. And we're realizing there are also new ways to produce mesons, ways that I didn't expect. And so some of this work will appear soon. But today, I just want to focus on one of these topics. And this is going to be about light composite dark baryons and its connection to long-lived signals. So the question is, how light can a strongly coupled dark matter candidate be? Bounds from self-interactions, sort of the classic book of its friends, suggest that the self-interacting cross-section has to be smaller than some critical value. Now, whether it's 0.1 or 1 doesn't really matter for this purpose. If you just imagine that or if you just take the naive dimensional analysis strength of the self-interaction of a strongly coupled particle, you would expect something of this size, and you turn that into a constraint on this scale, and assuming that all the scales of the problem are the same, namely the mass of the dark matter is of order this confinement scale, then you see that this is larger than of order 0.5 GeV. So this is sort of this lower bound, or otherwise you would have violated the self-interaction constraints. If the strongly coupled dark matter also transformed under the standard model, meaning there were, say, quarks buried inside it, like a neutron, dark neutron, then you expect an accompanying set of pions, charged pions, that should be present in the theory. And we know, we haven't seen dark pions at LHC or even more robustly from LEP. And so this sort of Drell-Yan production sets sort of a robust lower bound of around 100 GeV. And of course, there's even stronger model dependent constraints from LHC. So with those sort of thoughts in mind, here's the outline. So I want to talk about the first, or a realization of this idea that the self-interaction cross-section may saturate this this bound of 0.5 GeV. And actually it goes back to a paper by Morrison, Profumo, and Robinson from about 4 years ago called The Large N Nightmare. So some of you may be familiar with it, most of you probably are not. I'm going to talk about this for a little bit because it provides sort of a motivation for where we ended up landing with our own work. Once I go through this, then I'll sort of move into talking about the specific theory that we constructed here and what its connections are to the Large N Nightmare. And then what are the associated phenomenological constraints that we find. So that's the direction. Okay. All right, so let me start with Large N story. Large N Nightmare. So the Morrison et al. Work on the Large N Nightmare was the following construction. So they said, imagine you have a strongly coupled theory, SUNC. It has one Dirac flavor that they assume is light, much lighter than all of the other scales in the problem. In this light quark limit, you expect that the cosmological abundance would arise from two otherwise stable states. One of them is the minus baryon of the theory. This is in some sense the analog of, say, a delta plus plus if the only quark in the standard model were the up quark, only light quark in the standard model. Of course, at large n, this would naively have a spin at C/2. Of course, you need lattice data to be absolutely sure what is the spectrum of the states, and that the lattice state is in fact this. Large n arguments tell you that the mass of the baryon scales with NC, so NC times the confinement scale. And so this is one of the states, one of the stable states of this theory. The other state is the lattice meson. You can call it like the analog of the eta prime of the standard model. And due to its axial anomaly, you know that its mass also scales like lambda, but suppressed by 1 over NC, or n squared is suppressed by 1 over NC. So these are the two states that are primarily within the theory. You can ask how you get an abundance of one or another of these states. The assumption that they made was that their dark sector was reheated to some temperature. And in that reheating process, you produce both the etas and potentially some of the dark baryons. The naive expectation is that baryon, anti-baryon annihilation into mesons, being strongly coupled, would scale as sort of the geometric cross-section, so the Bohr radius squared. And if this, of course, is true, if this were in fact what you saturate, then you find that the annihilation rate, of course, may reach the unitarity bound all the way back to Reese and Kamiokowski years ago. And of course, this naively suggests that the upper bound on the mass of these baryons would be of order sort of 100 TeV. Again, this is sort of using updated constraints on the relative abundance. In fact, if the dark baryon had an order 1 magnetic moment, you can show that you actually saturate this value now. In other words, the existing constraints from xenon are already sort of reaching the scale. That's just an aside for it. It won't affect the rest of the talk, but it's a fun result that we found. When you go to large NC, things change, because Witten recognized long ago that at large NC and in the non-relativistic limit, fixed velocity, baryon and antibaryon annihilation is exponentially suppressed. So this cross-section not scaling like pi r squared, but is suppressed by, in some sense, the overlap of the quarks and the antiquarks from the baryons and the antibaryons, which is some small number raised to the nth power. So this is, we can write as an exponential suppression with some coefficient that we don't know. So something that we don't know. So if you imagine a theory, or if you imagine this large N nightmare picture, but for a moment, just imagine there were only dark baryons in the theory. This could arise, for example, if you had some other interactions in which the eta prime decayed. Okay, so just for a moment, imagine you do that. Then you can calculate what the relative abundance would be, and that's what Fukumoto and his friends did. You find that the abundance matches the cosmological abundance along sort of these curves, which is a function of this funny C parameter in the exponent. In other words, how much exponential suppression is there versus the number of colors. And so, and it's just some curve in this space. Interestingly, it doesn't depend on the mass of the dark matter. And this at least arises when you compute the freeze-out abundance of these baryons. The freeze-out abundance really just depends on the number of colors and this exponential suppression that they found. So from this perspective, there's a wide range of dark baryon masses that could match the relative abundance. And all you really need to do is to somehow find a theory that lands you in the proper place in this space. Of course, I did make one assumption when I said this story. I made the assumption that the etas don't contribute. But of course, naively, if I have no additional interactions, then the etas are stable. That's what I said from the beginning. So that would lead to, if the etas are stable, that would lead to a multi-component theory of dark matter. One in which there's potentially dark baryons as well as these dark etas around in the theory. And they explored that, this multi-component theory, doing the multi-component Boltzmann evolution. And here's just a couple of samples of the results that follow from this. So there's a series of parameters they have on the top of the plot. These are related to the effective strengths of the eta chiral Lagrangian, so the self-interactions of the eta. Depending on exactly what they took for these couplings, and as well as this parameter, which is the ratio of the dark sector temperature to the standard model temperature, which I'll come back to, then they end up with results of this variety. So there's a particular place in n, which is not necessarily an even or not necessarily an integer value of n, by the way, where you can realize that the dark baryons achieve the correct abundance. And of course, this is largely independent of eta for reasons that I just explained. Why? Yeah.
Can't you have other lighter global states?
So this then depends on the relative spectrum of the state. The blue balls are typically parametrically heavier than the eta at large n.
But for example, already in QCD, there is a sigma which would be lighter, right?
There's also potentially a sigma. Here, whether the sigma and the eta, the relative hierarchy, is again a sort of a, shall we say, a model dependent question. The assumption that they made in their theory was that just the eta was the lightest. If I don't mention it later, when we redid this for our particular theory, we also considered this sigma in its lifetime. So if I don't mention it, I'll come back to it. So in this space of just the eta prime and the baryons, what they found was that there is for n moderate, larger than QCD, there's a range for which you can match the relative abundance of dark matter from just etas or baryons, or potentially a combination if you happen to be in some two region. And the origin of this of the strength of these the origin of the shape of the line basically boils down to how the interactions are scaling with n. So the chiral Lagrangian typically is suppressed by 1/n. So as these interactions are further suppressed, you have to force n to be even smaller to match the abundance. The blue region is that which is excluded by self-interactions. And so again, depending on the different parameters of the theory, which set the strength of those interactions, you may be completely ruled out, or you may be allowed, and where you are in the space tells you where you can be with the scales of the problem. So that's largely what they were able to do, and to sort of show that you can have this completely decoupled sector, reduces the relative abundance of dark matter, off you go, which is potentially a multi-component theory, or maybe just eta products. Of course, they use the word nightmare in their title because it's a nightmare to detect. It doesn't have any interactions with us. So the only way to detect it would be modifications to lower scale structure through self-interactions. If you imagine the baryons were the dark matter of the theory, of course, you would need this additional dynamics to get the eta to decay. That's purely a matter of statement of if it were baryons, then this is a consequence you have to use. That adds complication, right? But the principal thing is there's no relation between the temperature of the dark sector and the temperature of the standard model. Again, in the absence of any other interactions. So that's why there's a parameter throughout all their plots they call eta. That was the ratio of the dark temperature to the standard model temperature. And so you can get an abundance that varies just depending on what the relative hierarchy of those temperatures. So in some sense, the relative abundance of the dark matter is subject to whatever that UV physics was that sets that dark temperature. This is where we came in, because we wanted to think about a way in which you could relate these temperatures and yet effectively realize this one flavor theory in the low energy effective. And so this has a funny name, which I didn't give it. And what I'll do is I'll talk about now a one flavor theory of dark matter that has in its UV a sector that allows the temperatures to equilibrate. Once you allow the temperatures to equilibrate, you set small interactions of the light sector fields with the standard model. And those small interactions are exactly then how you might be able to detect this. So that's the connection, and that's why we thought this was really fun and really interesting.
And what if you don't introduce one flavor, just pure glue dynamics? You still have the lightest blue ball, which is stable.
You do. And people have thought about that in other contexts.
So why it's better to have one flavor as compared to the scenario where you have only pure glue?
So the issue, I think, is how do you connect that sector's temperature to us? And if you do that, how do you ensure that the glue balls are stable?
No, the lightest blue ball is automatically stable.
It's automatically stable if I have no UV connection between the dark sector and us. But once I put in a connection, then it's possible that the glue balls will decay through higher dimensional interactions.
So your dark matter is not really a dark matter.
Precisely. Once you try to relate the temperatures together. It's not, I'm not giving you a theorem. I'm saying that's the generic result that you get when you attempt to go that way. Anything else? Okay, so our picture is there's a dark sector. I don't know, I was finding images on the plane last night. This is the first one I came up. It's some video game apparently. So we have this dark sector, which is a one flavor SUN theory, which we've already talked about. So it has this eta, it has this baryon and so forth. Standard model on this side with David's famous plot. Okay.
Walters.
Was that?
My editor made it up.
Your editor? Okay, well. David's collaborators. And then what we'll do is introduce this equilibration sector, which are basically heavy flavors that transform under the standard model and under the dark sector. What they will do is allow us to have a connection between the standard model and this dark sector, but ultimately this will have the characteristics that look very much like the one flavor theory that we start with, but just with suppressed higher dimensional interaction there. Precise construction is this. This is one of an ensemble of potential constructions you can imagine. What we ended up doing was just saying, well, let's imagine that the equilibration sector is a set of vector-like, lepton-like objects. In other words, they carry quantum numbers of, they're a doublet under SU2 and plus or minus a half under hypertrophy. Vector-like means I give them a heavy mass. That's the equilibration sector mass. And of course, they also transform into the dark sector color group. These equilibration sector fermions can mix with the one light sector fermion, this one flavor, through just ordinary Higgs interactions, because of course these have quantum numbers in the Higgs. So already at tree level, you can write down these small interactions between L and N. So L, the doublets, equilibration sector fermions, and the fermion in the light sector, the neutral fermion. And it looks something like this. So this is the mass scale of the light flavor, which for us we allow to be potentially light or moderately heavy, and I'll show you results within that range. Here's the equilibration sector, which will be heavy. We're talking TeV or so. Okay? And then a small, and then I said small mixing because the mixing is proportional to the bev of the Higgs, and with whatever the Yukawa needs to be. When you go from this theory into the hadron description, of course, well now there's a dark baryon like we had before. There's an eta, which we're also talking about, and here's sigma that I had mentioned before, and then potentially blue balls in other states. So there's an ensemble of potential states here to consider. In the heavy sector, it's essentially just these vector-like leptons that transform into color, but you can think of these as, for example, dark rose and other heavy mesons that are potentially producible at LHC. So the distinction between these two theories, and then I'll show you what the results are. So on the large N side, there were no interactions with standard models, so there's no way to define it. On this side, on our theory, we have dark baryons that have small interactions with the standard model. And so this will lead to small direct detection cross sections at neutral states. Here, the eta prime was stable in the absence of the dynamics. On this side, all of our mesons will be unstable. They'll be unstable again due to interactions with this equilibration set. Large N nightmare, of course, you didn't really predict the relative abundance of dark matter because the temperature ratio was arbitrary. You had to set that to some value. So now these temperatures will be equilibrated, at least at high temperatures, when assuming the universe goes through an epoch where the equilibration sector fermions are thermally produced. Here, they explicitly showed that you could get the abundance from, specifically the abundance of dark baryons through a symmetric freeze-in process. Now there's at least the possibility of doing a symmetric freeze-out process with the dark baryons. We have not actually done this in detail, but of course the exponential suppression that we found will work or ought to work here as well. So this new heavy sector does what? It allows for things like dark row production, which is otherwise known as Z primes searches. This is sort of mundane physics that LHC is already searching for, but that sets the scale that this must be larger than a few TeV, otherwise it would have already been seen. There is now a small interaction of the Z boson with the dark baryon, which you would naively think would be a complete disaster, because of course, if you had a full strength interaction, this would be really large. But this is suppressed by this small mixing over the equilibration scale in the fourth power. And this is just doing a direct calculation of how the mixing works. Finally, mesons, like the eta, but also the blue balls and also the sigma, are generically long-lived. And if I focus just on the eta for this purpose, the eta has a mixing, if you like, into the goldstone of the Z, which then couples to the standard model proportional to its mass. And so you get interactions, or you get decays that are very long-lived. You get mesons whose lifetime are very long, again, proportional to this parameter, this YV over MEQ to the fourth power, times an additional mixing, which is basically the difference between these two powers. All right, so these are the new components that you get. And let me just, in the interest of the last couple of minutes, I'll just flash the results and then wrap up. So this is the result that we find if we're in the light quark regime. So if we imagine, like Profumo did, that the dark sector fermion is light relative to the other scales of the problem, we find that if this YV over MEQ is larger than, say, 10 to the minus 2 or a few 10 to the minus 3, then of course Z exchange will rule out the theory from direct detection. But since it scales its theta to the fourth power, of course, there's this very, as the direct detection constraints get stronger, you only drop this down by a marginal. This is not a particularly strong result. If the eta decays too slowly, specifically decaying during BDN, then of course you'll screw up the predicted abundances that we all know and love from granular synthesis. And if you take that constraint, that's this sort of green region here, and it rules out all of this space, And what you're left with is sort of this white region that is available. And in the white region, we find that we can take this, the baryon mass to be as small as a few GeV, but sort of not arbitrarily small, at least before some of these constraints begin to cut things off. Within all of this space, the etas are long-lived, and you can see that they're long-lived at the level of thousands of kilometers or up to, meters scale for baryons that are 10 to the 2 or even hundreds of GeV, and then the corresponding eta mass here again, using large N to relate the scales. In this particular case, we fixed N sort of arbitrarily to this value and other parameters here. So this is what it looks like in the light quark regime. In the heavy quark regime, now the state that could become too long-lived is the glue ball. And so this rules out this entire green region, again, slicing off here relative to the direct detection constraint on the dark baryons, leading to the lightest mass you can get of sort of tens of GeV or so. And again, throughout all of this space, you expect the glue balls are long-lived at the levels of thousands to kilometers scale. This, of course, provides fodder for so when we kind of look for long-lived particles to the facilities and certain parameters. Okay, well, I'm out of time, so let me just wrap up with a quick discussion. I've thrown a couple of dark sectors that are thermally coupled to the sonic matter. Can provide a lightish dark matter candidate, lighter than you might have otherwise expected. Not though all the way as light as being able to reach the self-interaction band, the sort of 0.5 GeV. So we find that these things can be light, not exceptionally light. So it suggests that there's a whole different sets of ways of trying to look for these sectors. One of them, of course, is to look directly at the radiation sector, rose and other mesons. One is to look for the light meson decays, and potentially direct detection if you happen to be lucky, right at this. And of course, I already mentioned this point that the long-lived mesons provide other opportunities for detection. All right, that's it. Thank you. Okay,
so here you consider decay of the eta prime via the mixing through the non-zero Higgs bed. Do you also have a decay through the dimension 8 operator between this dark gauge boson and our gauge boson after integrating out this heavy what you call equivalence state? Is that negligible?
The leading interaction is dimension 6 because of this mixing with the old cell. So that would be even further suppressed.
But that is independent of the mixing, and I presume that if the theta is extremely small, that one dominates.
Yeah, that's true. If in fact that's right. Yeah. The trick is that the eta also yeah, let me leave it there. Yeah.
Yes. So since the self-interaction bond from the black plasma seems to be at least one of the key ingredients that you are playing with it. I just wonder if you go up to the 2 flavor or many flavor region, obviously you all of a sudden have a ion instead of eta prime, then self-interaction can get momentum suppressed hugely, right?
Yeah.
So it can get 8th power suppression of a P over lambda. So then it looks like you can easily just go down very easily. Rather, actually, it's better to go down because then you can get more suppression.
Right. So I mean, if this is then a matter of how complicated you make the model,
right,
and then as to whether those pions are long-lived enough to potentially then lead to other constraints.
Yeah, this will depend on the coupling to the equilibration sector.
Precisely.
Yes.
We did not explore more than one flavor.
Yes.
In this context.
Hi, thanks for the talk. If you don't mind, I'm gonna ask a question about the other groups.
Yeah.
You said they had freezing dark matter abundance.
Yes.
At least my naive version of freezing is standard model particles pump energy into the dark sector slowly and then build up.
Yeah.
If there is no connection between the standard model and that other sector, what do you mean by freezing?
Freezing from the etas.
So etas freezing into the baryons.
Correct. That's right.
And they deplete their own abundance, so.
Yeah, so the Etas will have their own self-interactions and they will have some degree of cannibalism as well. But the freeze-in abundance here is not, so it's literally you produce a thermal bath of the Etas or of the quark equivalents, and then it slowly freezes in the baryons from there.
Okay,
That's the origin.
thanks. Let's see.
So what was assumed about the N scaling of the quark masses versus, in your example? Is it important?
So the
large N limit doesn't commute with the light quark.
So the Eta mass is set by just the dynamical scale, right? So, suppressed by 1/NC. So the quark mass doesn't directly impact the mass of Eta unless its mass is heavier than the confinement scale.
We could talk later.
And so there will be two, so these two pictures were literally whether the quark mass was parametrically smaller than confinement scale or larger than. And then
I think the critical scale is not the confinement scale, but confinement scale divided by N. We could talk later.
Could you say very briefly again what the LHC signatures are, the Z prime or the Z prime like particles? So how does it decay?
Yeah, so this, there would be a series of vector resonances that are that would be similar to the Z and similar to a W prime that would be there. In detail, we haven't studied that exactly what those two signals are, but that's effectively you'll have vector mixing between the rho and the W and the Z of the standard model.
But could they go also to the dark sector baryons or dark sector particles and then come back to the standard model? Or
right, so then
they would predominantly go directly to the standard model.
They can go to either in principle. But there's within this context, there's always some move back into the standard model. And so that was the origin of us setting these constraints. 3T together with the observations.
Yes, so
That's
yeah, last question, but it seemed to me that for your story, the large NC doesn't play a much role. I can just say there's a strong couple dark vector. I set those particles and there's a separation of states. So you just borrow large NC to give you a scaling of the masses of those.
Yeah, that's right. And just to recognize that theory space didn't force us into any particular N. We ensured that N was greater than 3 just so that the barrier symmetry for the stability. But beyond that, we don't actually have an explicit restriction. It probably would enter if you try to realize the symmetric abundance of the baryons from this exponential freezing. But the problem with but of course, the standard issue with achieving the abundance, especially a symmetric abundance that has a small coupling to us, is that there's indirect detection constraints that you have to face as well. So, which we haven't touched. So that's the, that's it. Okay, let's move on to the debates. Well.
I sent you a Slack message. I think there's even more funny things. I think there are even more funny things that we have not discussed. We can just. Actually, no, unrelated. There is some connection, with a small connection, not quite. Yeah. We can talk. Probably that's relative.
I'm good. How are you?
All
right. Yeah.
Okay.
Let's do it, McCallum.
Let's
move over. They're glad to go tomorrow.
Still can't find a house like you.
You professor for a long time, right?
Right.
Indeed.
Buying it.
Yes, because there's also good companies that this can't be done.
These are parts of the universe of going. Where else do you universe of going? Yeah, I know it well. Personally, I haven't. We're all affiliated with Runaway.
I know, I've been.
I'll be there.
Sir G was in Israel.
As a lab, you know, it will be.
Getting a murder. Yeah, August, first August 3rd.
All right, so we should begin. So we're very lucky to have our next speaker, Giovanni Villadoro, who is going to tell us about the open string Axiverse.
Thanks, thank you very much for thank you for the invitation. So sorry for the change of title, so that I would be able to talk about more things, but then I realized that the program will not be able to finish even half of it. But so this is a paper that came out recently with my ex-postdoc Claudine, this is friend. This is the first talk about axions. I cannot avoid to start this with, as usual, this quantity problem. So that just to remind you that so this is a problem about why is parameter theta in the standard model. To measure one of the two sources of CPU variation in the standard model is so small, so the absence of observation related double moment put very severe bounds on this parameter, which happens to be basically the smallest dimensionless parameter in the standard model. So the smallness of this parameter, the way I see, is not as any other tuning problem in the standard model. This is a dimension 4 operator, so it's a dimensionless coupling, so it's not quadratically sensitive to new physics scale. On the other hand, so this problem is more similar to the flavor problem, which is why there are such very small parameters in the standard model. So, as you know, if you uplift the theta term to a dynamical field, the axion, QCD itself provides for a potential that to stabilize the axion to a minimum that exactly cancel the parameter, no matter what it is, minimizing the potential to the CP invariant point, and providing the axion a mass, which is related to the QCD scale, and the coupling of the axion to the standard model, parameterized by this decay constant parameter itself. So this solution of the small CP problem is probably the most elegant and, to my point of view, plausible. I like to formulate the solution of the problem in a slightly different way. So if you imagine that in a full theory of the universe, the theory should explain all the parameters that we observe at low energy, then you expect that to any parameter that we observe in the standard model, there should be a field that dynamically explains. So for all the parameters except the term, the associated field, for example, for associated to the gauge coupling or the UCAVAS, is quadratically sensitive to new physics. So you expect it to be heavy, and therefore the physics behind those parameters is expected to be like a very high energy. And this is compatible with the absence of observations of flavor correlation. This is different for the axion, which instead is not, at least in the standard model, is not quadratically sensitive to the high energy. So has a chance to receive most of its mass from QCD, from low energy QCD itself. So you can reverse the argument and say that the observation of no electric dipole moment is a hint that most of the axion mass comes from actually from QCD, and that basically cancels the And of course, this argument is very appealing because it's testable. It predicts a new light state that we in principle probed experimentally, although not so easily. And if such a state, light state, exists, we know that it's going to be produced in the early universe under relativistically from just the thermal bath that will continue as an effective, but also there is an irreducible contribution to dark matter, and so in principle it could account for all the also solve the dark matter puzzle and account for all the dark matter that we observe in our universe. As you probably know, there are two scenarios for the production of dark matter, Axion dark matter in the universe, which depends on the scale, the relative size of the scale of inflation, the maximum temperature of the universe, and the decay constant of the axions. So two scenarios are basically the scenario in which the pre-inflationary one, where the breaking of the PQ scale, the PQ symmetry happens before inflation, and the case where it happens instead after it. So in the first case, the abundance is uncalculable. There is a parameter that enters in the calculation of the abundance, which is the initial misalignment, misplacement of the action field with respect to the minimum, which is uncalculable. It's an environmental property of the axion field within the observable universe, and therefore we cannot directly relate the parameter of the model, in particular the mass of the axion, to the dark matter abundance. And in fact, almost all the parameter allowed parameter range for the coupling the mass of the axion is compatible with axion being 100% of the dark matter, almost basically for all values, depending on this initial misalignment. The things are different instead in post-inflation, because what happens is that after PQ is broken after reheating, the evolution of the field is such that they proceed towards production of topological defects. They proceed into some sort of attractor, which completely erases any information about the initial values of the axion. So in that case, there is a one-to-one relation between the value of the mass of the axion and the abundance, the relic abundance of non-relativistic axion. The challenging aspect in that case is actually to do this connection reliably. So there is a value that will explain the axion and dark matter to observe today. The particular value is still has some uncertainty. I will estimate this uncertainty nowadays to be 1 or even less order of magnitude, but still a lot of efforts are required if one wants to really improve the situation to a level that is useful for explaining.
Excuse me, so why does theta equal pi stop at a few times 10 to 9 GeV? This misalignment case, theta equal pi.
What determines this mass?
Yeah.
So this is obtained by trying to tune the initial misalignment as close as possible to pi, in such a way that isocurvatures do not kill you, even taking Hubble the smallest possible compatible with the axion mass.
I see.
All right, so another aspect of the story is the following. Of course, all I said works as long as, in particular for the solution of the symmetry problem, works as long as I said, the QCD provides the largest contribution to the axion potential, so that it minimize the potential, the axion field to the CP invariant point. So one could ask, what does it mean? This in terms of extra breaking of the PQ symmetry that you might have from other things. So in order not the solution not to be spoiled, you want that any other breaking of the PQ symmetry that will minimize the axion to a different value from this P1 should be smaller than 10 to minus 10 at the bounds on theta times the contribution from QCD, which is here parameterized by the topology of stability. So in numbers, it's around 0.2 MeV to the 4. So is this a strong or weak constraint? Well, now if you put this information together with the fact, with the lore that in quantum gravity there are no global symmetry, and you want to be fully conservative, then you will say that since in quantum gravity there are no global symmetries, at M Planck you should expect contribution as big as M Planck to the 4, and of course this is zillions of orders of magnitude larger than what you can afford to solve this problem. So in order to, so many people then try to get around this by construct the model building level models that to realize the PQ symmetry as an accidental symmetry, which means that if your low energy effective theory is such that you can apply operators that break the symmetry up to some order, and this depends on the bit content of your model, then you could afford, basically, you could be in a situation such that all these corrections are small enough. Of course, depending on the scale of FA, of the decay constant, ranging, let's say, from 10 to the 10 to GAT scale, the bounds of the higher dimensionality operator that you have to put becomes rapidly very, very strong. So you have to forbid the operator of dimension 10 or less in the best case scenario, low FA, or even operator up to dimensionality 40 in the worst case if you want to realize a large FA axion field. Of course, the models in this case become rapidly less appealing, and also the solution, the axion solution to the Strauss-CP problem, in the sense that it looks not as plausible compared to alternatives.
Susan, I don't understand. Gravity, let's say gravity destroys global symmetries, but its effects are suppressed by 1 over M Planck. Because gravity becomes strong only at M Planck, right?
But at M Planck, I don't have any symmetry.
Yeah, at M Planck. So it's already at this very high scale. Why do you need so many terms to suppress it? Why do you need to nullify the...
No, because I want to be smaller than 0.2 MeV. So the suppression is only in powers of FA over M Planck. So
No,
FA is as big as 10 to the 10. So if I'm going to be suppressed by FA over M Planck, and I need so many powers to be smaller than 0.2 MeV to the 4.
Why FA? It should be 1 over, it should be M Planck. Why FA?
M Planck over what?
M Planck? Instead of FA, you should use M Planck.
Yeah, M Planck in the denominator, but
In the
numerator there is FA.
Huh?
In the numerator there is FA.
In the denominator.
In the numerator.
Huh?
Numerator.
In the numerator, it's FA, and in the denominator, it's M Planck.
Okay.
So it's that ratio.
Ah, the ratio. Okay.
All right. So of course this argument are a little bit naive. In fact, all the arguments about the breaking of global symmetry in quantum gravity are non-perturbative in G Newton. So we shouldn't expect really, at least the irreducible breaking of global symmetry in quantum gravity are not powers of G Newton. Loops of graviton do not break any symmetry. So in this respect, then we can instead go to the other hand of the argument and say, oh, okay, but QCD already breaks this global symmetry. It breaks it by non-perturbative effect associated with the susceptibility, which are actually non-perturbative in G strong. After you embed, for example, QCD in string theory, this will be non-perturbative in G string, non-perturbative in G. So I could just say, okay, this is the way quantum gravity breaks the global symmetry. It breaks through QCD. I don't need to add anything else. And in fact, there are completions of axions in string theory for which this is the dominant break. So at this point, high quality PQ, Peccei-Quinn symmetry, is just a statement about the fact that quantum gravity needs to be completed a weak cavity, so that non-perturbative effects are exponentially small. In other words, you have to worry about PQ quality problem only in explicit TV completion of quantum gravity. For example, if you want to embed the full theory instinctively. So a prototypical example of how this works, here it's provided by extra-dimensional gauge fields. It's this string Axiverse. So the idea is very simple. Imagine you have extra dimension and gauge fields. Then you can associate the axion with the Wilson loop of the gauge fields in the extra dimension. This degrees of freedom behaves as an approximate Goldstone boson. Now, the fact that the actual local field, the axion, comes from a non-local object, the Wilson loop in the extra dimension, is what provides the protection for this for the Shih symmetry of the axion. In fact, no local operators in the extra dimension will generate a potential for the axion because it's a non-local operator. You need to propagate some charge fields in the extra dimension. So as long as all the charge fields in the bulk of these extra dimensions have a mass which is larger than the size of the extra dimension, all these contributions, which are associated to propagators that wrap the same cycles of the axion, will be exponentially suppressed, will be utilized. So this is the gauge theory interpretation of this movement. In string theory, there is also a rationale why there are no light charge fields that could have dangerous effects. For example, if you associate these gauge fields with the closed string sector of the theory, like Ramon, which shows P forms, under these gauge fields, the only objects that are charged are D branes or membranes. Their tension, since they are non-perturbative objects, is always a small G string are always parametrically heavier than M strings. So in particular, they're always heavier than the compactification scale, as long as the compactification scale is larger than M string. So there will be PQ breaking effects. In this case, will be suppressed by some volume factor and some G string. And as long as you are weak up in large volumes, these corrections are very small. And in some cases, they can be reparameterized in terms of the gauge coupling of that gauge fields and acquire a form which is typical for these effects, which basically match the continuation of small scale instantons in the unit. So some of the properties of this axion are the following. So realization of the axion of this kind automatically are associated to large decay constant. So the axion Shih symmetry that comes from these fields is always non-linearly realized from the four-dimensional point of view. And the associated decay constant is always parametrically larger than the compactification scale. So this is a good news for pre-inflation scenarios in which you want large FA axions. But it's a bad news for post-inflation scenarios, because in this case, it's very hard to have a calculable model in which you can restore the PQ phase. So you need to be able to go to temperature, for example, above the compactification scale, actually parametrically above it. In the case of the string realization, you really need to be able to produce on-shell D branes that acts as topological defects for the axion. These are non-perturbative effects, so it means that you really need to go to a non-perturbative regime in theory, which is highly uncountable. At the same time, you could have a phenomenological problem, because at that point you also be able to produce other non-perturbative objects like monopoles. Okay, so to go around this, it's not too complicated. So all you need to do is to assume you also have some localized charge fields in the x dimension. So let's assume that in the context I talked so far, you also add charge fields under the gauge field, which are localized. This is actually a generic properties of this type of compactifications. In fact, it's a required property if you want to realize the standard model. So the model has scalar fermions need to be localized in the x dimension. And they arise in various contexts. We'll give examples later. So now, if you have these localized fields, now let's consider two of them, say phi plus and phi minus, that have opposite charge, for example, under the bulk gauge field. Then you can build a gauge invariant operator. So you see that if you have localized, all the charge fields are localized, you cannot create any gauge invariant local operators. The only gauge invariant operator must be non-local, a combination of charges connected by Wilson lines. Now, beside the rotation associated to the gauge invariance, you also have the opposite rotation. Imagine you rotate the two fields with opposite phases. This transformation here, I call PQ, it appears as a global, it's not gauged, appears as a global symmetry. Locally, it's just a phase rotation, so it matches what is gauge invariant. So you cannot write any gauge invariant operator that is charged under this global symmetry. The only operator that are invariant and gauge invariant and charged under this global symmetry are of this type. This means that now you have emergent global symmetries which are exponentially protected, exactly like the one that we had for the gauge field itself. So if you have n of these fields, n minus 1 phase rotation would be the gauged one. Sorry, one linear combination of phase rotation is gauged. The other n minus 1 phase rotation remains as exponentially good global space. Moreover, the symmetry can be linearly realized in 4D. In fact, it acts on this operator linearly. In particular, the associated Goldstone boson after this operator gets evolved has a decay constant which can be parametrically smaller than the compactification scale, as long as at least one of these two BEVs is much smaller than the compactification. So this wanted to define the fact that this mechanism is actually generic, and it's so generic that it appeared already in the literature in various forms. There's a paper by Delgado quite long ago that actually implement the same idea in explicit 5D construction. I will present a similar construction that is better suited for my purpose, but basically the idea is the very same. So imagine you just have one extra dimension, you put a gauge fields in the bulk, U1, and two fields with opposite charges on the boundaries. And this realizes what I just said before. There is a phase rotation in which phi plus and phi minus rotate in the same phase, which is a global symmetry, which is exponentially protected. So if you want to realize the QCD axion, all you have to do, for example, if minimal KSBC form, all you have to do is to add also fermions on each side. The anomalies and gauge fields in the bulk, the anomalies cancel globally. The U1 global symmetry called PQ is anomalous. It's basically you have a KSBC sector on one brane and in the other one. The U1 symmetry in this case would be locally anomalous. You have to add a Chen-Simon stems to cancel the anomaly that flows on the other side where they are globally erased. Now, imagine that one of the two BEVs is heavier. So you can write an effective theory which only has one of the two factors, for example, Feynman. And this, at the four-dimensional point of view, just reconstruct the minimal KSVC model for the axion with one scalar field and one pair of characteristics. So in this way, you could complete the KSVC, the minimal KSVC model, in a way that is completely protected from quantum gravity effect of the global rotation. Of course, you can all the model building that we could imagine to do to solve other problems like the stability of the scalar field, with SUSY, gap, and exotics can be implemented very easily. In fact, this hexagon dimension doesn't need to be large, it can be at the gap scale or smaller. So the whole phenomenology follows the four-dimensional usual one.
That's the.
That's a thunderstorm.
Tornado. We're now learning. Can you say, there's one room. Go to the interior room.
We are.
We are interior. This is about.
I think we have fine.
Oh, we are at
That wasn't the simulation stuff. I think, but there was an entire city. There is a more minimal version of the model by just sending one of the verbs to infinity. In that case, it makes the boundary condition of this side Dirichlet. And at the end of the day, you are really left with SBC. So this leaves basically this, if you want, suggest a very nice way to actually extend this mechanism to any global symmetry. Now I'll give you the recipe to make any global symmetry in 4D exponentially good from the UV point of view. So imagine you have a 4D theory with a U1 global symmetry. You have charges operator under this U1 symmetry. So all you have to do is to gauge the U1 symmetry, put the gauge fields into a small hexa dimension with the Dirichlet boundary condition. The theory in 4D is exactly the same because there are no light modes for mu. But now, because the symmetry is gauged locally, we cannot write any gauge invariant operator which is local and break this symmetry. The only gauge invariant operator is going to be your local operators in 4D attached with the Wilson line that goes from one side to the other, which is non-local. And therefore, it can only be produced by exponentially small effect if all the charged fields under this mu are larger than the XL. Have a mass which is larger than that. So notice that in this way, the 4D global symmetry is not an accidental symmetry. You can write, in 4D, you can write operator that break, low dimension operator that breaks the symmetry, but they are just have exponentially small coefficient. So if you want, this is a way to reconcile the ancient practice of imposing global symmetry by hand in the EFT with the more modern law that quantum gravity breaks all global symmetry. So very rapidly, maybe just catch the UV implementation in string theory. Also, string theory is very simple. To realize this scenario, imagine you have two branes that intersect in 2 points. On each branes, there is a U1 gauge field. There are strings, light state, string state that are localized in the intersection, string that stretch from one brane to the other. These are the only charged states. In the back, the only other states are strings that stretch between the two. But if you want them to go from one side to the other, they become very heavy. So at the end, the only gauge invariant operator is something local again. And the breaking will be associated to the worksheet distance to the propagation of these strings from one side to the other, which will be exponentially suppressed by the area of this object, which is much larger than 1 as long as the separation is larger than this. There are also other effects like the brain instantons, and also those are exponentially suppressed as long as the two ends are separated in the string units. To realize the QCD axiom is very simple, just add a stack of D3 branes, and now you see that on each side, this reproduces exactly the matter content of KSBC and KSBC prime, so this realizes the 5D models that I sketched before. You can compute, estimate all the potential sources of breaking of PQC, and then they will be all exponentially suppressed. The leading one is the worldsheet instanton on this D brane, which actually scale exactly like small scale instantons, and can be easily parametrically suppressed compared to the topological. So now you can imagine that in a more realistic scenario, these branes intersect many times. For each intersection, there will be a global symmetry associated to it, which could be exponentially good. So if the scalars in these locations have expectation values, they will generate exponentially light axion, and this will basically is the idea behind the overstring axion. So the only last, this last slide, just to show that now it could see what are the implications of this scenario for the usual searches of arcs. And the important things to notice here is that from the point of view of coupling to photon, coupling to standard model is the usual story. But in the case this axion is a positive inflation scenario, so they have a lower pay, there is always zoo of way to detect them only gravitation in a completely model independent way. Because if the axion realize post-inflation, they produce strings, topological defect, they decay. So there will be effects from gravity waves that can be probed. There is a lower bound from the fact that they will overclose the universe if the decay constant is too large, that exclude all this parameter range. And there are effects on isocurvatures and so on. This is the QCD associated. Okay, I think I'm regular time, so maybe I'll stop there.
There's time for a couple of questions. Some questions. Yeah, go ahead.
So if I compare it with the models that implement it with an accidental symmetry, they typically explain the decay constant as some dimensional transmutation, right? That's another feature of those models. But here, the decay constant here would just be another parameter, right? Or can you relate it to the string scale or the scale of the extra dimension?
No, you could also do that. For example, here I was considering mostly elementary scale, this case this model, right? You could do the composite axion also in this way. So instead of putting the scalar phi plus and phi minus, you can put psi left and psi right, fermions, right? Now chiral symmetry is protected exponentially well. So there would be pion, if you want, as a mass that is exponentially small, and it can be an axion.
I see. Yeah. So
then you don't need a supersymmetry.
Yeah.
A question here from Graham.
Yeah. So the notion that global symmetries can be sort of restored in some sense in this way. Do you think there's any restriction on that? Like, are there any global symmetries I could concoct in a low energy effective theory that I can't? I can't imagine getting exponential suppression.
Well, yeah, it's always hard.
I know, that's what I'm asking.
It's very simple in this way to realize U1 symmetries. Non-abelians are a little bit more tricky, but can be done. But all the idea of this actually came from the way hierarchical Yukawa couplings are realized in string theory, which is basically the same. And in those cases, the Trevor symmetry is non-abelian. So in principle, it can be done a little bit more tricky. And I don't know what global symmetry, I don't know, maybe discrete symmetry, I will solve it out.
And also myself asking a question as well. How sure are you that in quantum gravity, even without, there cannot be some instanton that has logarithmic sensitivity to imply transaction, so that you get back to a law? How can you be so sure?
You are saying that the action is not power suppressed to the coupling.
Yeah, I'm not saying I know an example, I just mean like you're making a pretty non-trivial.
But sorry, in that case, it means that it's not non-perturbable. Because if you put a log in there, then it will be power.
But there are wormhole solutions.
That's why I'm asking,
Yeah,
yes.
there are wormhole solutions which are logarithmically sensitive.
Also, the wormholes are exponentially suppressed as long as you separate them string from implant.
But they depend logarithmically, like if you look at some solutions, like if you include the radial mode in the coupled Einstein scalar equations in Euclidean space, if you include the radial mode, there's logarithmic corrections.
But sorry, this is in pure
In
gravity.
the action, in pure gravity, yeah.
I'm saying that you cannot trust that estimate the moment you have a string is magnetically below and flat. Then in full M strings, they're all exponentially suppressed. That's the Shih.
Okay. Great. If there are no more questions, we should move to the next talk.
What's the second one?
Okay, so our next speaker is Antonio, who will tell us about non-invertible PQ symmetries and other things.
Thank you very much for the invitation. And thank you for Giovanni, who has given me a wonderful introduction to Axions. Although my Axion is going to be different than his Axion. So I'm going to talk to you about how to implement the alignment limit in a 2HDM using non-invertible symmetries. And maybe the next speaker is going to talk about that too, non-invertible symmetries, so that will flow. So non-invertible symmetries. So this was this is a paper we published last December with my wonderful author Seb. And it goes as follows. So symmetries, and we have had several talks this morning and now by Giovanni about symmetry. Symmetry permeates all what we do. Supersymmetry, the idea of a composite heat comes from the fact that asymmetry goes through a phase transition and so on and so forth. So in particular, I'm gonna spend a little time about flavor. So we don't understand lots of things to understand the model, but flavor is one thing. There has been a lot of approaches to understand matrices. One approach is to do Spurian analysis, and then you understand the hierarchy of masses, starting with the top to Kaplan, and you associate no Spurion to that, and then you start adding the Spurions, and then you can try to understand why different you have a search model, and this is nothing but a probabilism mechanism, and there has been also ways to implement the probabilism mechanism, including in high dimension. So another way is to try to understand the CKM and the PMNF matrices with textures. They are very different matrices, as we all know. CKM is almost an entity matrix, whereas the PMNS matrix is certainly not an entity because the identity, but you can have bimaximal mixing and assume some discrete subgroup that determines how that matrix comes about. A4 comes in there. You can also try to understand flavor using bottom-tau unification. Close to us this morning about unification. So bottom-tau unification exists in some form of BMSSM. And you could try to understand how the tau and the bottom you have are equal at the cascade and then running. And as I said, you can have extra-dimensional models to explain flavor. You can also try to gauge CC. You know. But what I want to turn my attention is to generalize symmetries. So generalized symmetries were discovered by mathematicians several decades ago, and only recently permeated to the world of physics. And in the last 10 years, people have been using this concept of generalized symmetries to do model building. So what is a generalized symmetry? So you extend the usual concept that we are all familiar with point-like symmetries, that you is the way we understand rotations, the way we understand time evolution in quantum mechanics, the way we understand gauge symmetries. So we treat these objects like point-like objects. So there are other objects, extended objects, but which don't loop. So then you can try to analyze the study and see what consequences have when you try to incorporate these extended objects and the symmetries associated with these extended objects. So in this talk, what I will try to do is to embed the usual PQ symmetry that Giovanni already introduced. But here I'm going to realize it linearly because I'm going to do it in the 2HDM. So the PQ symmetry is a U1 symmetry there that is linearly realized by the pseudoscalar of 2HDM. And I'm going to embed that into a continuous flavor group. That's a paper that Sungwoo said and claimed. And I'm going to use that model to try to get a 2HDM model that is naturally in the alignment limit. And the limit in which one of the two pieces in the 2HDM is aligned with the standard model. That's what the other. And interesting fact is that if we were to use this model to solve the strong CP problem, that's a big if. But if we were to do that, this pseudoscalar will be a realization of the Weinberg-Windsor physical action, because this action couples to show you how. So first, let me give you a very fast overview on generalized symmetries. Well, normal symmetries, you can view them as forms. So a zero-form symmetry is the usual symmetry that we know from point-like objects. So the associated current to a zero-form symmetry is a one current, is the usual current that we have in electromagnetism, and is conserved linearly in photons. Then you can generalize that to a one-form alignment predicate. That would be a usual line. In that case, this is a one form, or if you embed this in the usual geometry, that's a vector. So the current associated, it has two indices. So then you have G mu and it has conserved. And then you can have a two form. A three form could be a domain wall. And in general, what we see here is that the extended objects with d dimensions will couple to d+1 current. That in generally they are conserved. And that's the concept of symmetry. This is how we derive the concept of symmetry in the usual electromagnetism. Well, this would be what we call a generalized symmetry. So how these come about in field theories? Well, we know that in the UV with non-trivial dynamics, these extended objects could lead to IR theories where infinities are realized not by standard unitary operators, but as non-invertible objects. That's also why these symmetries are called non-invertible symmetries, because you cannot realize them as matrices in a group. So they are not invertible. So one example is QCD. QCD generates an instantons because of the variant number anomaly means what is subgraph observed in the anomaly will be Z3. And this Z3 is not realized in the usual way because you have extended objects with these instances that break the variant number to this conserved. So from the IR point of view, you understand this symmetry as a transformation of an extended object. Since it's an extended object, you cannot associate a matrix. On the other hand, if you go to the UV all symmetries are realized in an invertible way. And this is what happens. So these generalized symmetries have already been used to explain neutrino masses or as a solution to the strong problem by Sungwoo and Runaway. Yes.
What generalized symmetry are you talking about in the SM? Is it some Z6 one form symmetry or Z3 one? What is it?
What do you mean? The one that is conserved is as a.
That's a zero form symmetry.
No. How you realize this? How you realize this? How will you ended up getting a Z3?
It's a discrete symmetry.
But what? You started with a U1.
Yeah, just maybe J anomaly.
Yes, and then you have instantons.
Yes.
And then how do you, the instantons left the Z3, so you have to implement the Z3 so that the instanton is invariant. Instanton is an extended object.
It's a point.
No, it's not a point. It's an extended, it has size.
So is instanton charge
We
and
could discuss
Z3?
later.
But instanton is not a point.
It's a point in space. Well, it's it's localized in space time, no?
That is a configuration of.
But anyway, that's not how you define. But it's okay. Don't worry. Maybe it's just the language mismatch between how I think and how you think. It's okay.
We can.
Yeah, we can discuss later. Don't worry.
We can discuss how, but this clearly is that the fact that you have these non-perturbative objects are the ones that break the U1 variant to these conserved objects. That the instanton is invariant is this. I'm not discovering anything. This is very old. And it's something that was done before generalized symmetry.
All right.
This is another way if you wish to how instantons is as a invariant. Now I'm switching gears and I'm gonna introduce to you the other aspect of my talk, which is the 2HTM. The 2HTM is a minimal stateless standard model with one extracting sublet. In the 2HTM community, both phi1 and phi2 have the same hypercharge. That's not the usual way you do it in the MSSM. In the MSSM, you normally write phi2 or H down to have the opposite hypercharge of each tab. This is not supersymmetry, so you're allowed to write all the possible quantities that you have. I'm not claiming that I'm solving any hierarchy problem, but I'm trying to realize a particular parameter space of the 2HTM embedded into a theory for polar flavoring. So depending on the Yukawa structure, 2HTM, you have different models. So in the model we're gonna work with is a type 2 2HTM, which happens to be also the MSSM. The MSSM is affected with 2HTM. Yes, that means that you use one object to couple to upwards and the other object to couple to downwards. So LHC tell us that you have to be in the alignment. Why? Well, the measurements that we have had in the case tell us that it behaves like a standard model up to the main hyper. So one way to realize the alignment limit is to implement a PQ symmetry. If you implement the PQ symmetry, which is U1 symmetry transformation of phi1 and phi2, then all of these quantities vanish in the exact. These cannot be true because in the exact PQ symmetry, this implies it is equal to 0. Then you have Boston boson because once you break electron-weight, you also break U1 and then the pseudoscalar will be mass later. But we are going to softly break that. I'm going to embed this model into an SU3H 18 keys. And this is how we're going to embed the quarks, the two pieces, under this SU3H. And this is how we're going to realize the PQ symmetry. And the PQ symmetry is anomalous, and it's going to be similar to what happens with the Wagner number inclusive. These are the charges that you have the different objects that break the PQ with respect to the assignments that we have. So with these assignments, one breaking is So there have been people that have studied 3TM at Nausian, and you have paper with Silva Ferreira, they have analyzed all the possible parameters. And this is what they're called one of the exceptional regions of the 3TM. I'm happy to discuss probably what do they mean by an exceptional region, because it's not important in this case. So as I have already said, the LEC data suggests that one of the things that has to have standard model properties. So it has to be in the alignment limit. What we're going to try to do is that we're going to realize this in the 2HCM when you have alignment without Leah. For those of you who have studied the MSSM, the way you get the alignment limit in the MSSM is by coupling the second doublet, the MA going to infinity limit. And then yes, it's true that you align with standard model, but a phenomenology is that of a right hit and a head. Here, we're going to try to find points in parameters when you have alignment without. Again, Saber and Silva have analyzed different scenarios for such a result. General ICP, Peccei-Quinn, which is the one we're going to use, the Higgs family. But our goal is to try to embed the PQ symmetry in a UV model, making some use of a non-invertible symmetry. So it's a model that Seth and Sungwoo wrote for. So the people charges are anomalous with respect to a symmetry, but UCD instantons are going to break with symmetry to succeed in the same way that they break the barrier number. And we're going to embed this in a UV theory where color and flavor are unified, and the leftover PQ symmetry is going to be embedded in the following. The Z6, the Z2 is going to be invertible, and the Z3 is going to be non-invertible. So this is a model that it was written. This color flavor is unified model. These charges, the two Higgses are not charged under the color flavor. This is the C2 doublet, singlet, doublets. And these are the hypercharged charges, and I'm normalizing so that this is equal to 1, so then the usual normalization, you have to divide by 6. And these are the PQ charges. And then this is the object that breaks SU9, is in the 165. So this model provides a unified setup for color and flavor. And it's an attempt to explain both the Yukawas, both in the vector and the force sector. And maybe we could try to explain the CP violation. But the details for the rest of the talk are not important. This is just a UV model that has non-abelian symmetry, whose instantons breaks this non-invertible symmetry. And therefore, it generates a contribution to M12. M12 squared is 0 if the PQ symmetry is exact. And generated a contribution to M12 squared. For those sushi aficionados, M12 squared is not very different than being. Instead of doing a naive dimensional analysis of this breaking, I can use a technique that it was introduced by Chava in order to calculate the instanton contribution to this parameter. So here is how it goes. So lambda 9 is going to be the boundary condition where I define the value of this alpha 9. Then V9 is the bed of this Xi as race. B0 is the beta coefficient of this SU9, and C9 is the instanton density factor. So this is the value of M12 calculated with this instanton diagram. It depends, it's an integral over the instanton size. And this is the value you get, and you get the usual exponential suppression of the object you get compared to the bed that you use to break SU9. So you can plot this, and depending on the value of alpha 9 on the breaking scale, then this is the ratio you get between the M1, 2, and V9. So it's 8 or 9 orders of magnitude. You can also generate, in the same way, different couplings with insertions of M1. Okay, so then we have M1, 2 now. We have to know what is the spectrum that we get once we have that. Then This is in the Hegel single language, here, special, I forgot the name, ERPS4 is one of the regions of this UHDM. So the mass of the pseudoscalar is M12 squared by 2 divided by 2 sine 2 beta. For those of you who remember the MSSM, that's the useful one. The mass of the charged Higgs, the mass of the two Higgses. This is the value of tangent beta, and then cosine cosine alpha minus beta, which is the quantity that will tell you how much aligned or not aligned you are with the standard. So it depends on certain couplings in the two limit, lambda 1 is equal to lambda 2, but of course the running of Kaplan coupling will separate you from the exact PQ symmetry, and R is just a shorthand of these two quantities. So as I said, we have to account for the LHC data. So the LHC imposes MA to be greater than half of the mass of the Higgs to avoid bound from the invisible decays of Higgs or decays that we generate for leptons or for quarks. So then the current alignment condition is that cosine alpha minus beta has to be less than 0.05. Then we're gonna also require that tangent beta is greater than 5. So this implies, I say, deviating for the exact Z2 limit. But again, there's a Z2 limit for Riemann colors. So the prediction we get is that MA is greater than 120 GeV. We also predict in this theory that the heavy Higgs has a mass close to the pseudoscalar. And in this case, the quartic that this Higgs has is twice the value of the standard. In the standard model is 0.17, well, here is 0.30. And then in the last maybe 5 minutes, I'm gonna show you how this could also be the visible action that was introduced by White and Wiltshire a long time ago. So this CPO scalar, capital A, that realizes linearly the U1, if this model were a model for CP, or to explain the CP violation of the standard model to solve the strong CP problem, Giovanni was talking, then this is the visible function. Why is visible? Well, this couples to the standard model, like a 2H game, couples to. So if we could embed this higher model, not just in a model that addresses flavor and color, but also addresses a strong CP problem, then this would be an axiom, because the only breaking of the PQ symmetry comes from the instances of the system. And this IRPQ would be a non-invertible realization of the UV fundamental PQ symmetry. It has an advantage compared to the usual axiom because it doesn't have a problem with the quality. It doesn't have the quality problem. Because if we introduce the useful couplings that we can introduce, that will change the behavior of the axiom. If you expand this one, and this one is possible, then you have the usual cross potential proportional to M12 to the 4th, which is the one that breaks. But then what's suppressed here is the electroweak compared to M1, not FA. You get the electroweak. So then there is no a problem or quality problem in this case, or in this case, provided that you assume this way. If V9, the bed that breaks SU9 is less or C, that's equal to 10 to the 8 GeV, then this visible axiom won't have a point. Again, this is a big if because I didn't show to you the UV theory that will solve the strong symmetries. So then we conclude, symmetries are fundamental tool to understand nature. Generalized symmetries provide with an extra handle to try to build models, especially with one for physics. And in this talk, I have introduced the concept of non-invertible symmetries, and then I have applied to the PQ symmetry in a 2HTM. One can invent a 2HTM effective model in a UV complete model based on an SU9 favor color unification model. SU9 instantons break the non-invertible Z3 and generate a contribution to M1 to a square. So then the spectrum generated is in the alignment without the Kaplan limit of that was TM, which has a very interesting phenomenology. It can serve as an example of a single action solving the strong symmetry problem, again, provided that the UV theory indeed. So, people and there are lots of possibilities in model building and similar projects. Thank you.
Right, we have time for questions. Yeah, there's a question in the back.
Can you go back to the slide with the 2HTM results, the last one that you had? No, you had some values of the, yes, this one. What is the range that you get for MA? You say it's larger than 120, but that's the only limit you find, or do you find any preferred range? Because from what you're saying, all the implication marks heavy Higgs bosons should have about the same mass. And we know that in type 2 models, for example, the charged Higgs should be heavier than 550, 600 GeV, etc.
We didn't, to be honest, we didn't look into the bounds coming from the gamma and things like that. You're absolutely right. We didn't look into that.
I'm pretty sure that if you have all the three Higgses more or less the same, they must be above 600 GeV or so.
It could be that you are right. We were just more interested to see how low could you get, because this bound of 120 comes from cos of alpha minus beta being 0.05.
Yeah, you also allow for negative values, I suppose, for coordinate. Thanks.
Other questions? Yeah, John.
So I didn't quite understand why you get the alignment without decoupling. Is that you impose the phenomenological constraints to fit parameters, or the symmetry structure?
M12 is small. Actually, N12 already points you to alignment without decoupling. And then, of course, you have to really impose cosine alpha minus beta, 0.05.
Separate, right?
Separate. Yes. M12 square equal to 0 will give the perfect alignment, but you are ruled out. Because
sorry, M12 being 0 is not the line. I mean,
in this
the two Higgs have different masses. The beam,
no.
There is a mixing between the two Higgs and the mass of the
I'm
two Higgs
imposing
independent.
M1 because this is one of those cases that you impose M1 to equal to 0 and alpha. M1 square equal to 20. That's the Z2 that you also impose.
Other questions? I have a quick one myself, just to check my understanding. You mentioned the Z3 non-invertible symmetry. By this, do you mean a symmetry that acts like a standard invertible Z3 on local operators?
Yes.
But acts non-invertibly on some Swift lines? Is that what you mean?
Yes.
Thank you.
This is what I mean.
Okay. Other questions? Okay, there will be time to ask more during the coffee break, so let's thank you.
Yeah, I'm gonna use. You can take it.
Yes.
Yeah, let's use it.
Awesome. Let's talk a little.
Depende con calcolazioni sono in effetti.
Okay. Yeah. Okay, it's awesome. So our next speaker is Sungwoo, who will tell us about global aspects in the standard model.
Thank you. Thanks for the invitation, and it's a great pleasure to be here. This is my first time visiting Minnesota, and it's great to see many people, friends, and I know. It was a great pleasure, and I hope to talk more about it. Right. So today, I would like to talk about what I started calling today the global aspect of standard model, which is basically global form of a standard model gauge group. And here the goal is to convey why this is an interesting physics question to think about. Okay. To me, this has a sensitivity to the deepest UV of the fate of the universe, I can think of. And here the goal is to at least theoretically identify which aspect of theory, which kind of parameter, which kind of physics can possibly be sensitive to that aspect, which I will hopefully try to talk about. So this is based on two work. One was done earlier with Clay and Leah, and then the second part of the talk will be based on ongoing work with the data plan. Okay, so what is the problem and why I think it is important and interesting question to think about? So all the observable that we have about the standard model, every kind you can think of, is consistent Lie algebra of SU3, SU2, SU1. But if we ask question about exactly which group we are actually living in, we still have this ambiguity about this quotient factor, which can be anything of the Z6 or its sum. Which I will explain why this is the case. But before I explain how to technically see this problem, I just want you to make a 2-point about it. First of all, this question is about the question of a one-form symmetry of the standard model. So if you care about the symmetry, this is one of the symmetry of standard model, and you probably want to think about it. But probably more importantly, you might ask, so what about it, right? So if we by understanding the one-form symmetry, what we can learn about the fate of the universe. So really, the second point is about that. So by understanding or determining exactly which one-form symmetry of standard model we're talking about, we will have a sensitivity to a very deep UV of the universe. But before I jumping into this explaining the second part of it, let me first at least spend some time to explain why this is the question about the one-form symmetry of the standard model. All right, so this is a super brief review because we already have some review. So I'm just basically going to tell you the definition without even telling you technically how to deal with it. So zero-form symmetry is a symmetry that are familiar to you, which has a charged object, which is a zero-dimensional. Meaning, under the zero-form symmetry, local operators are charged in the spectrum. Obviously, if you take a local operator acting on a vacuum, you create a zero-dimensional object known as particle. So this is why we mostly deal with it. Now, for zero-form symmetry, obviously, for continuous zero-form symmetry, we have a one-form conserved current that has this form. Now, we can easily expand that to the p-form symmetry. So p-form symmetry is a charged object, which are p-dimensional. So we're talking about the extended object. In the case of continuous p-form symmetry, which are necessarily abelian, if you're curious, I can explain that. They will have a p plus one form current. Okay. Like I said, I'm not going to go into technical aspect of it, but I'm just going to state the fact for now. Now, the kind of one-form symmetries that are they will play an important role for my talk will be one-form symmetries appearing in the gauge theory, like in the standard model. So first example, let's take a SUN type of a gauge theory. Just to go for it, let me take a case where either I take a pure Yang-Mills or SUN gauge theory with only edge-joint matter. In that case, this theory has a specific kind of one-form symmetry known as a one-form standard symmetry or one-form electric standard symmetry. In the example that I'm talking about, it has a Zn electric one-form symmetry. So one way to see that is to note that any dynamical field of the theory under a zero-form center transformation, it shifts like this. Basically, it goes through Zn shift transformation, but for both gauge field and matter field transforming under the Antionio representation, they carry charge n under zero form center transformation, which means that the entire local operators are uncharged under Zn center symmetry. Okay, entire local operators are uncharged under zero form center symmetry. Now, since I'm talking about the gauge theory, I can look at the Lewison line operators of arbitrary charges. But all of the matter field or dynamical field carry charge n under the center. So they can strain out Wilson line whose charge is n or multiples of n. What they cannot strain is the charge of 0 to n-1, which means that I have a protected Wilson line carrying charge which are classified by the Zn. The existence of a one-dimensional object, which are topologically protected, tells me that there is a one-form symmetry. In particular, it is Zn. On the other hand, this theory doesn't have a magnetic one-form symmetry. So basically, instead of looking at the electrically charged particle, you just look at a magnetic part of it. So one way to probe, given gauge group, what is the magnetic one-form symmetry is to look at a pi 1 of that. You may recall that according to the Wu and Yang construction, this is construction exactly to look for what is the multiple spectrum of the theory. So by checking what is the allowed multiple spectrum, you can figure out what is the associated to the line. That is a one-dimensional line that carries one-form charges. So by knowing that there is no acceptable monopole line, you don't have a associated to the line. Therefore, there is no one-form symmetry. Magnetic version of the one-form symmetry. Okay, so now I will make it a little bit more sophisticated, which is the whole point of talk. Is that let's now consider SVM minus Zn. So I'm looking at a certain global structures. In this theory, first of all, there is no magnetic electric one-form symmetry. One way to see that is that this notation is basically saying that I had a global one-form Zn symmetry and I have gauged it. So it is a redundancy of a redundancy. Okay, so I had a one-form electric symmetry, global symmetry. I gauged them, so I removed them, so I don't have a corresponding symmetry. So there's no electric one-form symmetry. But I don't lose everything. Instead, I get emergent dual one-form magnetic symmetry. So I had a Zn one-form magnetic symmetry. And so this can be checked technically by just computing, by looking at the first homotopy group of this group. In fact, that is Zn. One physical way of seeing this feature is the following. When I gauge one-form electric symmetry, the Wilson lines become all gauge dependent, right? This stuff carries not gauge invariant under this transformation. So I have to get rid of them. Getting rid of them means that I only take a charge and stuff in the spectrum. But in order to censor the Dirac quantization, when I project an electric state other than charges multiples of n, I have to include a magnetic state that carrying charge 1 over n. But the means is that now I'm enriching the theory by having extra gauge configuration that gave me magnetic charge of 1 over n time. So if you now square this naively, in a naive sense, that means that your instantons spectrum gets enriched. Now you have a fraction instantons, and you have that. All right, so far, this is just the ingredient which I'm going to be using the rest. Okay, so what is the problem and why this is interesting? I said that this is a question of a one-form symmetry standard model. Hopefully that's clear by looking at this. So for one way to check this is the following. The fact is the entire standard model matter. Okay, Q to the plus H. Q to the means Q, U, D, L, etc. Q to the plus H. If you take a Z6 zero form center transformation generated by all these generators of Z3, Z2, Z6 of the U1 hypercharge vector, the fact is that if you add this on entire standard model matter field, they are basically neutral. Which means that these Z6 associated Wilson lines cannot be screened because none of the dynamic charge exists to be able to screen those Z6 Wilson lines. That means that we have for instance, if I take gamma to be 1, I have a Z6 protected Wilson line. That means I have a Z6 electric symmetry. If I gauge some of them, for instance, if I take a subgroup ZB of Z6, which means that I'm turning this much into a magnetic symmetry, rest being remained as electric symmetry. So this is really a question about the one-form symmetry of standard model. Now, what makes it more interesting to me is the following second fact. This is about the UV fate of standard. So let's consider, famous or whatever your favorite great unified theories. Okay, SU5, Paris-Salam, trinification, whichever kind you want. Now, here, important fact is that when this theory flows to the standard model, it comes with a specific global structure. So for instance, first class, SU5, SO10, when it matches on the standard model, it will come with a Z6. Paris alarm will come with a Z3, unification will come with a Z2. Now, so really, to me, the physics question to me, beyond this more formal aspect of it, is that can I find any, even in principle, theoretically, observables in the infrared that can be sensitive to this gamma factor? So to test why this question is powerful, suppose I manage to find a one observable and I can observe that to say that gamma cannot possibly include that 3. If I can manage to do that somehow, I can sit in the IR basically saying that these theories cannot be realized in nature. I think that's a very strong statement to one can make. Now, because this is such a powerful statement one can make, that means the price is high. In a sense that this is non-trivial sort of game to play out. But nevertheless, I strongly believe that it worth the game. All right. So therefore, in the rest of the talk, my goal is to convey that my recent thought about this question: what are the possible observables and parameters of the theory can possibly be sensitive to this gamma factor?
But this is just a statement of the intermediate breaking, right? Because I could embed the trinification even into higher.
So, for instance, if you're thinking trinification coming from SO10, for instance,
yeah,
if this will come with extra Z3 coming here.
I see.
Therefore, it is consistent with this picture.
I see.
So even you can test that whether this trinification is coming from on its own, or it should come with something more bigger unit.
I see.
Well, it doesn't fit in SO10 or anything, but you said.
It's
For instance, SU5 can come with SO10. Anyway, so whenever this can come down from it, then when it reaches onto this intermediate phase, it should come with, for instance, Z2 here, Z3 here.
I see.
Okay, so in the rest of my talk, I will tell you first of all Axion story, and which aspect of Axion can be sensitive to the global structure. In the second part, I will tell you about electric cosmic string in V-quad, because this will not be topological strings, but they can possibly be sensitive to this gamma factor. All right. So let's consider Axion coupled to standard model. And bravely, I'm not going to motivate at all. Axion is cool, so let's go with it. So Axion coupled to gluon with L3, Axion coupled to electric weak sector L2, Axion coupled to hypercharge with L1. Again, the question is, I want to keep track of any parameters and features that are sensitive to this factor. Okay, so for now, let's first consider, just to begin, gamma to be 1. In that case, SU3 instanton and SU2 instanton must be integer valued. And then I can use Dirac quantization of hypercharge. Therefore, you learn that L1 to 3, which are parameters appearing in the infrared, should be just integer. So here, you don't get much of a constraint yet. Now, in the rest of the talk, in the first part, I will just state, instead of showing how to get it, this L1 to 3 must satisfy certain quantization condition depending on the gamma. So that will be the first part of the statement. Second part then is that, building on top of this feature, there's a certain symmetry. It's a non-invertible symmetry, but I'm not going to go into any technical detail. There's a certain kind of generalized symmetry of Axion, general version of the shift to symmetry, which also depends on the gamma, which means that there are symmetries appearing in Axion theory. Therefore, you might hope to get certain selection rules in infrared physics, which can encode, in principle, this gamma information of the unit. Third, I won't have time to go into it at all. Therefore, from this, then I will derive, in principle, we can derive that there is a certain Axion domainable spectrum, and their properties and their fate, which I'm not explaining, but basically, some of the domainables cannot be regular type of it. They will have certain weird property, which I will at least state, and then how to kill them will all depend on the gamma property. Okay, so those are basically the first part. So you already know what I'm going to at least state before we lose. So here is the first of the result. So this is a list of the quantization condition of this Axion coupling constant for each chosen global structures. Okay, so this is a lot of complex expressions. Let's look at it. Okay, so suppose gamma is Z3. Then, first of all, the L1 appearing in the hypercharge coupling must be multiples of 3. If not, it cannot be Z3. Okay, and then this particular combination, L1 plus 6 times L3 has to be multiples of 9, for instance. So I don't know yet, okay? But suppose we can possibly determine, this is how you can possibly determine that, but suppose you can possibly measure somehow these numbers. Okay, that's the dream of a whole axion physics. Then at least you can check, look at the table, which one is this is consistent possibly, for instance, right? Then for this particular example, obviously, you can check and you can quickly realize that this can only be consistent with the gamma being either one or two. So by actually doing cavity experiment or something at super low energy regime, you can at least say something meaningful about the unification, for instance. I'm not telling you how we can possibly determine this. Here I'm just creating or providing you a map between condition to the common information. Okay, so that's the first part. The second part. So now I'm going to tell you about certain symmetries. Once again, I'm not going to spend time on explaining technical aspect of it, but I'm just going to tell you. So first of all, if Axion coupled to just SUN without a global structure, then this K you can realize as a basic anomaly coefficient. So Axion coupling, this transimus interaction is nothing but Weisman-Witten term for ABJ anomaly. So at this point, you realize that U1 hit PQ, out of which Axion is born, is explicitly broken down to ZK, regular type of symmetry. And then you can connect that statement to a spectrum of domain wall. So if Axion get a potential when this sector condenses, then you get a K degenerate vacuum, and therefore you get a K domain wall that probably looks like something like this once instanton condenses. However, if there's a global structure, like I said, you have an extra spectrum of instanton, fraction instanton, and if you do careful analysis, you expect that there's a further breaking of symmetry down to Z K mod n instead of just ZK. And you might say, then what does the domain wall spectrum look like? But in reality, if you do more careful analysis than that, actually, just like this, but again, I'm not going to go through. In fact, full symmetry is actually, worth of a ZK in a sense of set, not as a sense of a group, because non-invertible portion of this symmetry does not satisfy group property. So I have a ZK worth of a symmetry in a sense of set, but there's a ZK mod n, which is group-like symmetries. So therefore, ultimately, we know that the picture is that in that theory with the global structure, Axion domain wall is not just single kind of domain wall. There are more regular kind of domain wall we used to think about. There's also some weird kind of domain wall, which I start call non-invertible domain walls. You might say physically how they are different. This is an important question because if I were to test, using the Axion physics whether there's any global structure in the standard model, now I need to dig into the properties of these domain walls. So this is alternative way of thinking about that. But so let me just jump on. So this I'm showing you a regular, usual kind of domain. Okay, suppose there's this beautiful naive Axion domain wall through which Axion experiences usual invertible kind of phase shift. Okay, let's also imagine that there's a non-invertible kind of domain. By which I mean when Axion passes through this wall, now it has experienced special kind of phase shift known as a non-invertible phase shift. Now the question is physically, what are the differences between what we have been dealing with so far versus what we are newly discovering? The key difference is that we believe because the associated symmetry operator associated with the non-invertible symmetry must host certain three-dimensional topological degree of freedom living on it. You can think of it as really like anions living on this three-dimensional world for you. So in principle, if you know how to cut this data, it should have an edge mode flowing through this edge of it through the anomaly influence. And this you can view really as a cosmological realization of a fractional ponormal state. So if Axion exists in the universe, and then coupled to the standard model with certain global structures, then we are talking about the existence of certain Axion domain walls who has a certain three-dimensional any degree of freedom, and they will have a fractional ponormal material. Now, right now we are discussing heavily to really make this physical existence of this any degree of freedom on the Axion domain wall as a solid ground. We'll
Excuse me, may I ask you a question? Because I'm not fully don't understand that in full. So is the difference between these two walls on the left and on the right cannot be measured in any, cannot be noted or observed in any local measurements.
Very good.
Because these global effects which are discussed on, it's only possible if you make a highly non-local measurement. If you know, for instance, if you compactify some hour space or some topology non-trivial, and locally, if what we do in experiment, we have a beam on one side of the wall, then we let it go through and let's assume somebody, but it doesn't measure the whole structure of the wall.
All right, so let me make a two comment along this direction. So one, what we are thinking right now is that when QCD phase transition goes through, Axion domain can form. And if we are living in a universe where standard model gauge dependent non-trivial structure, this type of wall will be formed. Now, what we are trying to do is that, for instance, in the presence of such three-dimensional any degree freedom, they will interact non-trivially, for instance, with the monopole or some other object. So we are formulating theoretically what are the possible selection rules on the topological defect dynamics. Once we have that at hand as a theoretical determination, we can make a phenomenological, predictions about that. Okay, we are getting there, and we are not completely having yet a set of observational prediction yet, but we are determining, running now theoretical determination of conditions they have to satisfy. That's comment number one. Comment number two, this is more of a speculation level, but it turns out that some of the condensed matter systems, such as axionic insulators, topological insulator, mathematically realize the same structure as this. Now the question is whether cosmological axion we like can possibly mix with those condensed matter system, all right? Because effective field theory is described with the same sort of mathematical structure. Whether we can use that, as you were asking, as a lab test, whether we can do that or not. I don't have an answer. We are trying. That's all I can say for now.
No, there's big difference because in condensed matter, the existence of the boundary is a natural phenomenon. We always have a finite size sample to do measurements. It always have boundaries. If you are speaking about cosmological aspects, this is not so evident. And if you don't have edges, of domain walls, if it goes continuously from one side of the universe to the other, this is much more difficult to find out anything about global structure.
Yeah, so this is a more difficult question. This is therefore reward is larger, right? Because if we can manage to sort it out this theoretically and possibly make an observation, by sitting at the QCD energy scale, we can say something about the Gauss scale physics. So reward is huge. Obviously, like I said at the beginning of the talk, I'm playing the hard game. I don't expect there's a systematic easy path to follow to make a prediction and measure can be done. All right. At the moment, as community, I think that we are still in the phase of understanding theoretical structure. Okay, phenomenological prediction is the next step, and I'm very much enjoying the process. Okay, so let's move on. So here is a set of like I said, asymmetries, axion symmetries as a function of a choice of global structures. So the notation here, yes, is that there's a full set of non-invertible symmetry, including usual invertible kind. The whole point, you don't have to look at the detail. Whole point is that a symmetry of an axion of the low energy effective field theory does depend on the gamma choices. So it is in principle sensitive. The question is, how do you map this into a set of observables, basis of observables they can possibly determine this? All right, so for the sake of time, I'm gonna move on. So like I said, I won't have much time to talk about the fundamental spectrum, but there's also very much exciting things to talk about. Instead of delving into a third point, I want to move on to the second point, because I think I have 5 minutes. Okay, so now I'm gonna switch gears to talking about now pure standard model physics. Okay, that will do the great. So here the goal is to see if there is an effect, physics effect existing in pure standard model that are sensitive to the global structure. So that's the goal here. This is quite preliminary. So any feedback or questions are. So what is the game here? Game is to note whether standard model Higgs at all, encode any secret about the global structure. So why do I ever expect even this is possible? first observation is that Higgs, our Higgs, carries non-minimal charge under U1 hypercharge. Okay, so in units of a product of the charge, it carries 3 units of hypercharge. So what? So you may be familiar with the fact that if you have a U1 gauge theory with a scalar carrying charge n, which condenses, then such a theory, so this is a photon with a charge n, angular mode of the Higgs, and the charge n coupled with the photon. This theory flew to infrared to what is known as a Zn gauge theory, otherwise known as the BF theory. Okay, so there's a topological phase in the deep infrared. That theory has a two-form symmetry under which B2 is transformed, but that's not important. The point is that there is a Zn classified cosmic. Okay, so if you have a condensing spontaneous breaking scalar which carries a non-minimal charge, then it leaves out in the infrared imprint of a cosmic string, which is capturing that charge event. The third observation is the following. Now, instead of considering abelian Higgs model based on U1 gauge group, if I consider U1 mod ZP, so I'm testing whether this physics is sensitive to the global structure, then one can show explicitly that this theory now flows to Z M mod PBF theory, which means that now this theory in the infrared has a cosmic string, which is instead of a Zn, it has now Zn mod P. So we learn from this exercise or this observation that topological defect spectrum is or can be sensitive to the global form of the gauge group. The question is whether such a thing, such magic realizes in Sano. So here's the play. So we take a Sano model, SU2 times U1 broken down to U1 ENM with a gamma, where this gamma can be either 1 or Z2. Here I will play the game with the approximation, then I will approximate this as U1 times U1, broken down to U1. Because I'm looking at the U1 subgroup of SU2, which is a Z in the photon direction and the broken down photon. That's what I'm focusing on. This effective field theory, and then I will comment on whether I make a mistake by approximating this, which will play the crucial role in the last part of the talk. So this effective field theory can be described as this. There is a photon hypercharge, there's a third direction of SU2, and then there's a Higgs carrying charge 1 under U1L, charge 3 under U1 hypercharge. This is a double abelian Higgs model. Now it is useful to make the change basis along the direction of broken direction, 1, 3 direction, and the orthogonal direction. Okay? If you do that in the U basis Q1, Q2, then Higgs carries charge 0 under photon direction and 10 under the Z direction. But there's a subtlety. So it turns out that this change of basis has extra redundancy in the gauge group structure because this doesn't satisfy modular transforms. Anyway, that's technically yeah. So now what I know is the following. If I consider a standard model without a discount factor, meaning this being 1, then this theory, after the electrosymmetry breaking, broken down to this phase. So there's a photon phase, there's a Z10 PF theory sector with a non-trivial quotient. If we consider the state of theory with a Z2 quotient, then we'll flow to effectively Z5 PF theory. So that's fact number 1. So with the only single approximation I did, this is the finding. So naively, at this point, you'd expect that therefore, with without a quotient, we expect a Z10 electric string. With Z2 quotient, we expect Z5 electric string. However, that's not the end of the story. So we have a fermions, and these are the charges under U1 1 and U1 2 after the change of basis. Do you note that they carry charges 2 or multiples of that here too, which means that each of the U1 1 and U1 2 they have only Z2 one-form symmetries because they can screen all the Wilson lines except the charge movements. So anyway, then the question becomes, we had a Z10 BF theory or Z5 BF theory. They have to couple to this set of fermions. So the question becomes BF theory coupled to matter. Then you can ask what happened to those topological defects. To do that, let's recall the following. Here is a Zn gauge theory known as again BF theory. And this one has a Zn one form, Zn two form, and under the two form symmetry, we have a cosmic string. Now, if I introduce a fermion carrying charge P coupled to the U1 field here, then this symmetry is broken down to CC. Basically, and you can view it as a charge of a scalar, and then you have a fermion with a charge P, so symmetry is broken down to this design. Okay, so there's a reduction of symmetry because of the presence of the dynamical fermions. So then what happened to us is the following. Here's the standard model once again with gamma equal to 1, there's a Z10. Gamma equal to Z2, Z5. Now, if we take into account the fact that we had a charge 2 matter sector coupled to this theory, then operationally or effectively, in this sector, we are still left with the Z2 somewhat topologically protected strings. But in the case of here, where gamma is Z2, there's no any cosmic string left out. Okay? So far, every analysis is solid except the fact that I made a one assumption that I approximated this one. Yes, basically I need a 1 minute solution. So let's summarize. What was the summary so far? With a single assumption that if I can do this approximate analysis, which means that I forget about the threshold effect at the electric scale. Okay, I forget about the massive W, massive Higgs effect. That this is acceptable analysis, but that's crucial analysis, approximation to be dealt with. Anyway, under that single assumption, what I found is that with the gamma equal to 1, I expect it to have Z2 strings. With the gamma equal to Z2, we don't have any strings. Now, but like I said, it's important the fact that this is actually part of the SU2, and this is crucial because that provides us actual destabilization mechanism. You might say that's a bad news now. I took a hard time to figure out cosmic string spectrum, but I just destabilized them all of them. But it's not, I think, it's all bad news. Now, in the limit where this is a stable analysis, I have a picture like this is Hubble patch. I have a cosmic strings with a electric magnetic flux. I mean, photon magnetic flux supporting those strings. But now, because it is actually coming from SU2, this is not stabilized. There's a cosmic string with a magnetic flux passing through. It's not stabilized, which means that they spread, and then they form all of this good cosmic string at the beginning. They spread out, which means that they will turn into a distribution of a cosmological magnetic flux. And there's a difference. Okay, if it is gamma equal to 1, we expect to have a certain level of cosmological magnetic field produced. If gamma included Z2, we don't expect to have that production. So here, the upshot therefore is that by carefully studying cosmological magnetic field production during the electric phase transition, obviously we have to take into account the evolution till today, and the size of that and distribution of, in principle, I don't know, I don't have a precise estimate yet. In principle, can encode information about this Z2 factor within the same conjugation. Anyway, so that's all I wanted to say. I will just start with showing my conclusion. Thank you very much for your attention.
Yeah, I've heard a few questions.
Yes.
Could photon trapping be like an observable if it had period of
photon what? Say it again.
Photon trapping?
Yes.
If this had an associated like charge density distribution.
Photon trapping, are you calling photon trapping for this, or what do you call photon trapping here?
I'm saying like is that a potential observable?
So
photon trapping was associated with defects in this global area, maybe away from such that.
All I can think about regarding electromagnetic effect is that these strings are supported by non-zero magnetic flux passing through that. Okay, I'm not sure if we can call it a photon trapping or not, but that's where electromagnetic effects are, locked in. And I'm making a statement that the size and the existence of that depending on the global structure. Probably I didn't catch your question. I'm happy to chat.
How many measurements did you need?
I don't know. So I know that there has been good development and then progress both observationally and theoretically to understand the cosmological magnetic field production and evolution. Right now, I'm catching up the literature and studying how I might possibly connect this direct question to observation.
One more follow-up question. Is this similar to, or what would be the difference between a fixed skyrmion versus like a free skyrmion in this?
Skyrmion, let me see. So in the electricity breaking phase, if you integrate the top work, in principle, in that non-linear model, you can have a skyrmion. Are you talking about that electric skyrmion or something else?
I'm wondering if a fixed skyrmion tells you anything about your cosmological.
Oh, in the QCD phase of skyrmion.
Which skyrmion?
Just like a fixed skyrmion?
No, but you have to say from where. I mean, you don't just get it free, right?
What generates the skyrmion?
What?
What generates the skyrmion?
What generates the skyrmion? Yeah.
Like a magnetic field, a defect.
Oh, I see. So do you have I don't know whether you have condensed matter background, but yeah, in the condensed matter background, if you have a system that you can create a vortex and stuff like that, you can in principle also have a skirming configuration. So here, I don't know exact same kind of thing exists, but all I can say is that in the electric phase, if you integrate out the top work, then you can generate the non-invertible model, and that thing in principle have a skirming term and can possibly support the skirming configuration. There has been some study along that direction, but I'm not sure if that can possibly encode this information. That's a good question.
Other urgent questions? I have some, but I'll save them for coffee. All right, okay, let's pause. We're due to start again at 4. Is that right? Roughly. Thank you.
No, wait.
Yes. Unification, is anything left?
If you gotta make it
Yes,
so that's
you could just say it's SU 5 times. We are going to more than that.
So that is part of the that I did.
Okay, so this is
yes, this domain will you found it by okay, so give you gravitational overlaps. On top of that,
give me Giovanni start part of no, sorry, not Giovanni. The middle talk.
Find you a non-invertible
It's not, so again, the singlet coupling blowing up, one issue of the coupling application, but also the other thing is, if it blows up, remember the flavor scale, right? Where you can write down operators giving take care of it, right? So, which that scale is 100,000 T. So your singlet coupling blew up before that. Singlet coupling blowing up, so this means okay, that's the cutoff. But if it blows up below 100,000, then immediately the question is, what about take environments? So that's again what I mean by crisis earlier. Nobody can hear these stories. Also, we have upscale, safety communication, flavor. Yeah, so this singlet example, using it to get many of the went back in the land. There, you just say, okay, fine. We have a little bit. As long as it doesn't go below 10 TeV, okay. If you go below 10 TeV, then of course you get correction. You like to it, yeah, that kind of. But people always ignore flavor. You know, this kind of flavor hierarchy. So don't bother about flavor. So again, the coupling blew up at 10 TeV or 100 TeV. If you write down operators suppressed by 10 or 100, while in flavor and CP, you're going to be 10. But nobody was bringing. Well, everybody knew about it, but we were not trying to pull the big picture. So. So we should, are you around the rest of the work? Yeah, we should keep chatting. I think this motivates me to go back to your paper and see what you said about.
Right, yeah, please,
Or if you actually dig up a reference. So I did look at your, maybe the GTM paper, including the follow-up.
Yeah.
But maybe you have even more subsequent.
Yeah, I'm curious to check our paper that we had specifically on the Higgs vector to see if there's anything. I think there we were considering much higher messaging scales. I don't think
Right,
there's any.
and you had some work after the thesis stuff.
Yeah.
Trying to really explain the one.
Yeah.
But again, with light source,
Like, yeah, see these skills.
Right.
But you use Atom? Right. But then, did that work or?
Well, yeah, we have models where you can get Atrons, even at tree level.
I see, gauge mediation.
Yeah, age mediation plus.
I see.
And.
Actually, that's actually good. Maybe but I can.
Yes.
Because I was about to say that, this A terms, as you know, usual gauge mediation, you don't get large integers. So that's the problem.
Extra stuff.
Yeah. Yeah, so again, we also, well, we are doing something beyond.
Yeah, I don't think it actually touched down in Minneapolis,
I think
but there's.
what I like is just to repeat that.
I think, yeah, there's one that touched down in West.
At the same time.
Like,
Way to get the terms, same as.
I don't know, the geography of the West. So.
same.
I
It's not that you're doing something
So,
separate.
when there's a thing like that, it means they can see.
That's the.
Of the video. I don't know, it doesn't look like a funnel cloud, but I'm not.
I'm glad you like.
Where actually in Wisconsin?
Yeah, so yeah, so,
Just southeast of New Richmond, Wisconsin. But I think the one that triggered the warning was the funnel cloud over Minneapolis, or at least the warning on everyone's phones. But I don't, if it touched down, they don't have.
Usually there was sort of a heat dome effect in large cities.
I did not know that, but that makes a lot of sense.
Is why often tornadoes ravage just the suburb that is just outside the really sort of urbanized zone, which tends to be the poorest suburbs.
Oh, no.
Tornadoes are really just
Yeah.
cool.
They're really classes. Yeah, I was about to say, oh, that's good, they don't need population centers. but-
Why do you take so many photographs? You've been doing this for years and you have 10,000 photographs of every conference you've ever been to?
For the record, they will stay forever.
But that would make more of a good story because.
Oh, I will give it to Megan and she will put it in some, our Institute website, so it will be accessible.
Because, these photographs are kind of meaningless now, but they will be great in 30 years when somebody says, that was so-and-so as a grad student.
Yeah.
The guy who won the Nobel Prize, the woman who won the Nobel Prize is here. There she is as an undergrad.
Yeah.
Don't.
No. Make one more.
You see, you are destined for greatness.
Maybe.
Me, I don't want to be in the photographs because it's just a sad story. I wrote two papers with this guy and then that was it. Career death.
Well, I hope not.
You, huh? I meant you.
Yeah, well,
You thought I meant me.
I'm barely vertical, yes. Yeah.
I remember once driving you in Maryland.
Yeah.
Somewhere, and you had to stop by your parents' place.
That's right.
And they came out of the house, we were in the driveway.
Yes.
I don't remember why on earth that happened.
Yeah.
But.
Yeah.
Somewhere else. I don't know where. Yeah, no, yeah. You don't come back very often, do you?
No.
Well, there you go.
Yeah, I mean, I
You're
come
just
back.
comment about failure.
Yeah, my research is a bit distant from those of Maryland.
Yeah.
They are.
And even though they are. We're talking about.
I mean, I come to the DC area quite frequently for family stuff, but like, it's harder to stop by the university. I have a kid as well. Makes sense to me.
They get in the way, I've heard. But in the end, they pay off well. They're good investment.
I'm having fun, that's for.
How old is yours now?
4.5.
Is it a boy or a girl?
It's a boy.
So you have a 4.5-year-old boy.
Yes, he's very energetic.
And what is his name? No. Make him Never.
Yeah.
No. It's never been like on the shoulder.
No, yeah, I'm very.
1.5 year old.
Oh, okay.
And the team is often working from home. So,
Well,
we're on Zoom with kids.
well, certainly during the pandemic, the time baby comes.
The afternoon session. We just had 2 more talks to make it through, and we'll start with Leah's talk, Runaway Gravitational Production of Dark Photons.
All right, thanks for the introduction. And first of all, thank you so much to the organizers for putting on this great conference and inviting me to come speak. So I'm going to talk to you about gravitational production of. The main takeaways from the talk I will start with, just in case you fall asleep for the rest of it, here's what to take away. This talk is going to be based on 2 papers, which you can find the archive numbers there. And I should also say that this is all in collaboration with these wonderful people, Rocky Cobb, Evan McDonough, and Christian Capinelli. And so the main takeaways from this talk are threefold. So first, I'm going to generically, hopefully convince you that gravitational particle production can produce dark photon, dark matter. Secondly, if we add non-minimal couplings to gravity for the dark photons, this can cause problems, including ghost and runaway instabilities. However, there's what we call a stable region of parameter space where we can avoid both of these problems and get production of the correct dark matter relative abundance. Okay, so I know many folks in this room are very familiar with the idea of gravitational particle production, but just so we're all on the same page, I'll just give a brief overview. So cosmological gravitational particle production, or GPP, as I will call it for short, is based on the very simple idea that the expansion of the universe leads to particle creation. And so this is a very old idea going back to even Schrodinger in the 1930s. And in particular is relevant during inflation in the early universe, where if I have the inflaton field and some spectator field, the non-adiabatic expansion of the universe during inflation will create particles of my spectator field. And so the kind of simple way to think about this, just in terms of basic quantum mechanics, is to consider 2 sets of operators at early and late times, which I'll call AA dagger early and AA dagger late, which are not the same. So by early, I mean kind of beginning or before inflation, and by late, I mean at the end or after inflation. And so if I act my early time annihilation operator on the vacuum, I of course get back 0, as I would expect. But if I act the late time operator on the vacuum, I do not get back 0 because these operators have evolved due to the expansion of space. And in kind of the standard quantum mechanics way, this corresponds to particle creation. And so I can relate these early and late time operators via Bogoliubov transformation, these parameters alpha and beta here. And so there's a simple way to write the parameter beta in terms of the mode function of whatever my spectator field is, which I'll call chi. So I can write down the Bogoliubov coefficient beta squared in terms of chi in the following way, where omega here is just the dispersion relation in terms of chi and its derivative. And then from beta squared, I can calculate the particle number density as a function of k, and then the co-moving number density. So this is not the only way to do this calculation. There's others that I think you'll hear about later, but this is kind of the standard procedure. Okay, so I'm specifically going to talk about gravitational production of dark photons. So a dark photon, as we all know, is a massive spin 1 or Croca field, and I will use those terms interchangeably. So I have my dark photon with a mass and a field strength F mu nu. And so in the context of dark matter, dark photons can appear in a couple of different ways. So dark photons are often thought of as a portal to the dark sector. So I can have some kinetic mixing with the standard model photon, with some kinetic mixing parameter epsilon, where I have a mixing of the field strengths. And then there are a variety of observable consequences that come from doing this in some of these papers here. But we can also think about dark photons as a dark matter candidate in their own right. And they can be produced by gravitational particle production, which has been shown in a variety of papers going back about 10 years by several different groups. This is, of course, not the only way to produce dark photons as dark matter. There's other mechanisms like freezing or misalignment, et cetera, et cetera. But I'm going to focus on GPP. Okay, so the specific scenario that I'm going to be interested in are dark photons, which have non-minimal couplings to gravity. So I wrote down on the last slide the Proca action, which is just these first two terms here. And now I'm going to add these two additional terms, which non-minimally couple the dark photon to gravity. So I'll have this term here, which couples a mu to the Ricci tensor via this parameter C1. And then I'll have a term which couples to the Ricci scalar. This will couple to the Ricci tensor via C2. So these are just two dimension 4 operators, which in kind of a generic EFT characterization, I can add to my theory. If I take C1 and C2 to 0, I of course get back my minimal theory, just minimal Proca. And then if I turn on these corrections, we have the non-minimal theory. And so, as I said, one can generate, one can just add these operators, which obey the symmetries of the theory. So it's a perfectly well-defined EFT. But we also expect these types of corrections to be generated from things like loop corrections. And so now I have my non-minimally coupled theory. And so there are two questions to ask. So the first is, how does the addition of these two non-minimal coupling parameters impact dark photon production via GPP? And I should also say there are these other two nice papers that came out around the same time as ours that also looked at aspects of this question. And then, as I alluded to earlier, there are some instabilities that arise when one does this. So what are the allowable values to avoid instabilities and then also to produce the correct relative abundance of dark matter? So for the rest of the talk, I will focus on answering these two questions. Okay, so the main effect that adding these non-minimal couplings has is to induce time-dependent effective mass for the dark photon. And there are two of these mass terms, which I'll call MT and MX, which on an FRW background can be written in the following way, where here M squared is just the Proca mass, R is the Ricci scalar, and H is the Hubble parameter on FRW during inflation. And so these two parameters appear in slightly different combinations in these two, this MT squared and this MX squared. And what you'll notice here is that these masses are not only time dependent, they're evolving in time, but they're also not necessarily positive definite, and this can become important later. Okay, so this is a massive spin 1 field, so there's 3 degrees of freedom. There's 2 transverse modes, which will end up being kind of subdominant, but I include this here just for completeness. So the transverse mode equation can be decomposed in the following way in Fourier space, where A is the transverse mode parameter, K is the co-moving wave number, and here omega squared just has the following form, where A is the scale factor and MX squared is the time-dependent effective mass that I showed earlier. The longitudinal mode is a little bit more complicated. So you'll notice here, first of all, the longitudinal mode has a non-canonical kinetic term, which depends on A squared and MT squared. So in order to canonically normalize the field, I will define this new parameter, chi, and the parameter kappa, which I define like this, also in terms of MT squared and A squared, in order to arrive at the mode equation, an action with a canonical kinetic term. And so this looks very nice and simple, but this omega squared here is actually hiding a bit of complexity. So omega squared here is dependent on the effective masses, their derivatives, second derivatives, and R and H and their derivatives. But really the important term to focus on here is this leading K squared term here, where you'll notice that omega squared has this modification in K squared corresponding to a evolving sound speed. So the sound speed is not necessarily 1 in this. Okay, so the first potential instability that I'm going to focus on are ghosts. And so of course a ghost is when your theory has a wrong sign kinetic term. And so as I mentioned before, these dark photons, when you have a non-minimal coupling, has a non-canonical kinetic term with this parameter kappa squared. So kappa squared is of course also time evolving and not necessarily positive definite. And so if kappa squared becomes negative, then your theory will propagate a ghost, which is of course a problem. So in order to avoid this, we would like to ensure that kappa squared remains positive definite throughout the entire evolution of the particle production. So throughout inflation and interleaving. So this is of course a K-dependent statement, but in order to be most conservative, we want this to be true for all values of K, all values of K. So we need to require that the effective mass mt squared remain positive definite throughout the whole evolution. So that corresponds to this combination here, remaining positive. And so what this does in the C1, C2 parameter space is to carve out a region in the upper left quadrant here. So here, just to show as an example, I'm taking a limit where m goes to 0. So this parameter mu I've defined to be m over he, where he is the Hubble parameter at the end of inflation. So this is a dimensionless quantity. So in the limit that mu goes to 0, the ghost-free region for C1 and C2 is this wedge right here. And so as long as we remain in this parameter space, the theory will be ghost-free. There is another problem though. So there's also what we call a runaway instability. So in addition to a ghost, this theory also has tachyonic behavior. And so you can again see omega squared here, which is of course a complicated time evolving function that can oscillate and become negative. So of course, having omega squared less than 0 is not necessarily a problem. This also happens in the gravitational production of minimally coupled scalars, for example, and leads to an overall enhancement in the particle production. But here, because we have a time evolving sound speed, it's a little bit more complicated. So again, the sound speed here is just the coefficient of the k squared term, this mx squared over mt squared. And I've shown this here for a couple of different parameter combinations. So the black curve here is just sound speed is 1, as you would expect in a minimally coupled theory. The blue curve shows a choice of parameter combination where the sound speed is oscillating, is not necessarily 1, but it remains positive definite. So you see there's a big oscillation here, right around the end of inflation, and then some smaller oscillations. And then lastly, here's in the red, we have a choice of parameters where the sound speed becomes negative at some point in the evolution. And this negative sound speed, when it oscillates through 0, leads to what we call runaway production. So this corresponds to the black would just be the minimal theory, the blue would be some enhancement, and then the red is this kind of runaway instability. And so this looks like the following. So here I'm showing the spectrum of particles and k as a function of the co-moving wave number. So the blue here is the minimal theory. This is what you expect if you set C1 and C2 equal to 0. And then the red here is what we find when the sound speed is allowed to oscillate for those same parameter values that I showed. And what you see is that at large K, there's a very dramatic enhancement in the particle number. And it runs away at larger and larger K, which is obviously a problem if we want to kind of have physically reasonable particle production with this theory. Okay. So, and so the way that you can think about this is by looking at the structure of omega squared. So here again, I'm showing 3 examples of what omega squared looks like for the minimal theory when the sound speed remains positive definite, and then also when the sound speed becomes negative. So for the minimal theory, you can see it goes as k squared and then a squared m squared. And so even in the minimal theory, it's actually still oscillating through 0, and that's fine. On the left, we have a low k mode, I'll call it, and on the right, we have a high k mode. And so you can think about particle production happening in this case, in that every time omega squared oscillates through 0, we obtain a burst of particle production. It's kind of a simplified way of thinking about it. So of course, on the left here, we can see that we have oscillations through 0 in all 3 of these cases, which is what we would expect to see. But then at larger k, on the right, because we have the negative sound speed in this red case, we continue to get particle production and oscillations through 0. When in the other two examples, the particle production has basically shut off at ik. So that's what leads to this significant increase, which at again k is 10 is like 15 orders of magnitude. So this is clearly an issue if we would like to understand particle production in a way. So in order to now avoid this runaway instability, we also need to require that the sound speed squared remain positive definite, and in addition to the ghost-free condition. So we already required that mt squared remain positive definite to be ghost-free. So now for the sound speed to remain positive, we also need to require that mx squared be positive definite. And so in this m goes to 0 limit, which I'm showing again here, the runaway free region of parameter space is this triangle here on the right. And so what you will notice in this particular limit is that there is no overlap between the ghost free region and the runaway free region. So if you take the mass to 0, the only acceptable choice of parameters are C1 and C2 are equal to 0.
Can I ask one question? So what is the correct way of thinking about in the parameter space where either I have a ghost or runaway? Is it that theory is ill-defined, or if theory is defined but our calculational ability is breaks down? Which way I have to think about that region?
Yeah, so good question. So here, thinking about ghosts, the theory is just ill-defined. And then the runaway, the theory is well-defined, but there is something breaking down in our perturbation theory or our EFT.
Does the ghost-free mean that there's no hysteresis?
Sorry?
Does ghost-free mean no hysteresis? And does runaway free mean that there's no Umklapp scattering?
Sorry, could you say that a little bit louder?
Does the ghost-free imply that there's no hysteresis? And does the runaway free imply that there's no Umklapp scattering, and that leads to the large NK?
Well, so in the ghost-free region, right, we're just avoiding propagation of unphysical modes. And in the runaway free region, you're avoiding basically like a gradient instability.
So there's no differentiation between imaginary modes and real modes.
Right.
But are you talking about condensed matter? You're talking hysteresis in the condensed matter point of view?
Yeah, like a soft mode instead of
And that's difficult to translate to this language. I think you are.
sounds similar to light mode. Yes.
Yeah, we can chat after so I can understand the translation between the. Okay, great. Yes, so if we want to avoid both of these problems, we need to avoid both ghosts and the runaway. So of course, for considering phenomenology like dark matter, we don't in fact want we don't want to take m to 0, we want m to be finite. And so fortunately, for m larger than 0, there is in fact what we call a stable region, where there's some overlap between these two wedges of parameter space where we can avoid both ghosts and the runaway instability. So here, this is showing m over he is 0.1, and you can see this is a zoom in of this very small region here, where we have an overlap between these two. And then here, taking m over h is 1, there is a larger region of the parameter space that in C1 and C2 scales like m over he squared. So for larger and larger masses, you have larger and larger corresponding stable regions. Okay, so I will take a quick aside to think about what happens here in early reheating. So for everything I've discussed so far, I've assumed that reheating happens much later than the characteristic time scale of the particle production, such that it doesn't make a difference to the end number of particles that are produced. So one might wonder if I have reheating happening earlier, how that might alleviate the runaway. And so the runaway is again controlled by this r over h squared in the effective masses. And so for what we call late reheating, what I just described, r over he evolves like this. And you can see for early reheating, where alpha reheat is just a reheat over the end of it, a at the end of inflation, the evolution looks a little bit more suppressed. It's not oscillating as wildly, which may lead one to think that this will ameliorate the runaway. However, what we find is that it does not. So here in the black, this is the original case that I showed. And then in the red, this is looking at an earlier reheating. And what we find is that it does actually improve the runaway a little bit, but it certainly doesn't turn it off. So it's now 10 to 12 orders of magnitude compared to the minimal case rather than 15. So early reheating does not actually solve this problem. Okay, so fortunately, as I mentioned, there is a stable region of the parameter space where we can avoid both of these problems. And so for the last few minutes of the talk, I will discuss what goes on in that region. So we're now going to restrict ourselves to what we call the stable region, which is ghost free. So MT is larger than 0, is runaway free. So X squared is larger than 0. And then we'll also require that the sound speed squared is subluminal. And so that restricts us to this region of parameter space. Where now C1 and C2 have been scaled by mu squared. Okay, so if we now want to look at particle production in the stable region, what we find is that there is an enhancement, but not runaway, compared to the minimal theory. So here in the cyan and the purple are the transverse modes, just to show that there is a pretty substantial enhancement in the transverse modes, but still very subdominant to the longitudinal modes. This is showing just one example of the evolution in time of one particular mode in K, and the kind of final value you can approximate at the end. And for the longitudinal mode, there is once again, in this particular case, a modest but non-runaway enhancement in the particle number once we turn on non-zero non-infinite couplings. And so if we look at what this looks like in the full spectrum of particle production, here I've shown the variation of just C1 setting C2 to 0. So again, the blue is the minimal theory, and then I'm increasing Then increasing C1 along the C2 is 0 axis. And we can see that the peak shifts over to higher K and gets larger quite substantially. And then on the right, excuse me, I'm holding C1 fixed to this green value. So C1 over mu squared is 0.5. And then increasing basically the minimum oscillation of the sound speed, which corresponds to changing C2. And so you can again see that there is a very large enhancement as that first oscillation in the sound speed gets closer and closer to 0. And so this is just to again show what this parameter space looks like. So here I've shown the stable region and contours of minimum sound speed. So this is taking along contours of whatever the minimum value of this first oscillation is. And so we can see that as you get closer and closer to the edge, the sound speed gets closer and closer to 0, and we expect that there will be a large enhancement in the particle number. So from this, we can then calculate the expected relic density from the end of inflation to what we would expect to observe today, where this is now dependent on the mass of the dark photons, h at the end of inflation, and the reheat temperature, as well as the co-moving number density. And so we look at this along contours of minimum sound speed oscillation. And here you can see that basically as one approaches the edge, there is a large enhancement in the particle number as the sound speed gets closer and closer to 0. And so what this does is it allows us wider flexibility in the parameter region where we can get the correct relic density of dark matter. So again, we have this big enhancement as we move outward in the parameter space. And so this allows, because this is also dependent on h, the scale of inflation and the reheat temperature, we now are able to open up that parameter space a little bit more because we can also change C1 and C2 to get kind of the correct value of the co-moving number density, such that omega h squared over 2 is 1 to get the correct relative density today. Okay, and in the last minute, I will just summarize. So I discussed how adding non-minimal couplings to gravity for a dark photon field will lead to ghost and runaway instabilities in gravitational particle production. The limits on the parameter space in C1 and C2 to avoid that. And so in this ghost-free and non-runaway region of the space, there are a wide range of parameters where we can obtain the correct relative density of dark matter. And then the addition of these non-minimal couplings allows for a wider viable parameter space for this theory. So with that, I'll stop and take any more questions. Okay, questions for Leah? Yeah.
So a couple of questions actually. If you go into your runaway region, the degree of runaway must still be at some point limited by the energy density in the inflaton itself. So is the problem there that you would effectively convert all the energy of the inflaton into these dark photons, in which case you would have a huge energy density, but there's not a real singularity there, right?
Right, yeah, it's that basically you would expect, some huge overdensity of these dark photons.
And then you're taking fairly large masses for the dark photon. What happens for much smaller masses?
Yeah, so this actually, generally when people think about gravitational production, you think about like masses of order HE. This actually works down to around 10, in the minimally coupled case, down to about 10 to the minus 7 EV, depending on, of course, what H and T reheat are. So even for like relatively low masses, you also expect this to happen for the dark photons.
All right, thank you for a very nice talk, but I just have a simple question. When I think of sound speed, to me, it's a thermodynamic concept. I just missed, I'm sorry, I should have probably asked this right at the beginning. What do you mean by sound speed for these quantum?
Yeah, so sound speed, I guess, I just mean the propagation speed.
Just their dispersion relation? Okay, and just if I may be greedy and ask a follow-up, what is the range of masses? It can come down to 10⁻⁷ eV on the low side, but how high can you go?
On the high range, it can be up to about 10⁻⁻13 GeV. So
Near
maybe a
the
quarter like
highest.
HE. Yeah.
Okay.
So there's a wide range.
All right, maybe one more.
Is this expected to be cold, warm, or hot dark matter?
So this is cold.
Yeah. Okay, let's thank Leah again. Great, and next we're gonna have Sebastian, and he's gonna tell us about TBA.
Variance. Brain astrophysics.
Variance. I didn't really time it right.
He can't even show us his dog.
Let's choose to mirror.
I already chose them.
Well, you didn't choose wisely.
Yeah. There's something like this is really from it all goes from the talk time. Which sound you
You want to read it for you? They'll send you. Doesn't read it.
I'll flip over it. Finish on time. It's difficult to get to the restaurant.
But there's, it's not that close.
It's in 1 hour.
Yeah.
Well, we have to get back to the hotel, leave the stuff, and then
Okay.
take a taxi or whatever.
Okay.
Oh, that was real TV? Okay.
Yeah. Sort of bad timing, but.
So, first of all, thank you to the organizers and thank you all for your patience with technology issues. I missed an email, and so my talk title was listed as TBA. But we made that work through a group effort over lunch. And so I'm going to tell you about how totally basic assumptions allow you to infer the detectability or not, as the case may be, of gravitational waves under those assumptions and at certain frequencies. So before I get into the meat of the totally basic assumptions that we're going to get on, I want to try and motivate, I don't think I need to motivate this part of the question, but maybe this part of the question. Why should we be interested in gravitational waves at higher frequencies than the ones where we have already seen them?
And so part of the motivation for asking this question is that in the back of my mind, I always have Jeff Goldblum saying, yeah, but you can do it, but should you do it? And I'm going to try and convince you that we should do it, but it's not going to be easy. So far, what we've seen in terms of gravitational waves is gravitational waves that tell us something about the recent universe. We have seen gravitational waves emitted by in-spiraling black holes, neutron stars, combinations thereof. We might have seen something of primordial origin if we think that the PTAs have seen gravitational waves. That's still to be determined, and probably the most plausible explanation for that signal, if indeed it is confirmed, is supermassive black holes. So still something from the relatively recent universe. But we are interested in what happened before today. As particle physicists in particular, we're most excited about what happened in this part of cosmic evolution. Also interested in what happened between here and today. But for that, we have photons. But for what happened before the cosmic microwave background, one of the best ways, or maybe one of the only ways that we can actually make direct measurements of things that happened at these early times is if we see gravitational waves that were emitted during those periods. Now, you might ask, why would you expect gravitational waves to be emitted? Hopefully this audience wouldn't ask that question, you would know the answer. But let me nevertheless describe a little bit about the spectrum of expected gravitational waves for those who are not initiated. So if we're talking about cosmological gravitational waves, as I was on the previous slide, there's typically a one-to-one correspondence between the frequencies of the gravitational waves that you would observe today and the temperature of the universe when those gravitational waves were produced. There are, of course, caveats to that statement, but this is a more or less true analogy. Meanwhile, if you're thinking about astrophysical gravitational waves, there is once again a correspondence between the scale of the object that is generating those gravitational waves, here I'm denoting it as lambda origin, and the frequency of emission, right? So if I have a binary, then you know that the frequency of the emitted gravitational waves is associated to the size of the binary, and the size is then associated, or at least the peak gravitational wave emission is associated to the mass of the objects in said binary. So I'm mostly going to be interested in stochastic gravitational waves, but I'll also mention tighten up those statements about astrophysical gravitational waves in just a moment. So at high frequencies, we actually expect there to be a couple of gold standard signals from within the standard model that provide us with something to look forward to. Although maybe it's something that many, many generations hence will have to look forward to, as we will see. So this comes namely in the form of the analog of the cosmic microwave background, but in gravitational radiation. So the same thermal plasma that generated the anisotropies in the CMB that we observed would have also emitted gravitational radiation. And when it emits that gravitational radiation, the resulting radiation inherits the thermal spectrum of the plasma that originated it, and the amplitude of that signal would be associated to the maximum temperature the universe ever reached. And so if you were able to measure this, you would be making a direct measurement of what the highest temperature the universe ever achieved. Exactly where the frequency of this peak lies also depends on the number of degrees of freedom that were available to that plasma at that time. And so you would also be making a measurement of whether it was just the standard model at T of 10 to the 14 GeV, or whether there were a ton of other particles in the plasma at the time. There is an analogous process, again, plasma fluctuations from our sun, being the nearest star. This is going to dominate over other stars, that will also produce gravitational radiation. And there, the peak frequency or the max frequency is about the temperature of that plasma. And so you can imagine that this is at even higher frequencies than what I'm showing on this. So that's in the standard model. But we're interested also, or maybe more so, in ESN. So there we know of many different scenarios that can lead to gravitational waves that would produce a stochastic spectrum that would have arisen in the early universe. So here, just to give you an example, because it's been discussed already today, a network of cosmic strings would generate gravitational radiation. Typically, it's got some sort of plateau structure, which would be up to about 1 gigahertz or lower, depending on the maximum radiant temperature. Meanwhile, if you had phase transitions, which we haven't heard about yet, but maybe we will later in the workshop, you would expect a sort of peak gravitational wave emission that is related directly to the temperature that the universe had when that phase transition. So here I've normalized to the Lisa band because that's the one that we often hear about in the form of the electric, if the electric phase transition was first order, you can easily see that if you go to, let's say, over kilohertz or higher, you're quickly probing very, very high temperatures, and therefore very, very far in the ESM. So I would argue that generically the signals that one might expect to see, these ones being very low amplitude, if you see stochastic gravitational waves that are not generated by astrophysics, then you're actually probing DSM cosmology, and therefore it's something worth doing. In particular, high-frequency gravitational waves allow you to access the earliest times. In the case of astrophysical gravitational waves, if you have binaries, then, like I said earlier, the gravitational wave emission frequency is associated to the binary mass, but also its size. Here I've normalized to gigahertz for historical reasons, for me, not for everyone else. But you can see that this would be some sort of BSM binary of black holes that would produce these very high frequency signals. One can also invoke the presence of new light bosons, in which case to not add too many BSM ingredients. Not add too many BSM ingredients, I'm normalizing here to a solar mass black hole, in which case all I need to add is the mass of the boson, that is the order 10 to the minus 12 eV, maybe lighter if you take a heavier black hole. But all that to say that if you see signals that are not clearly stochastic in nature, but that are above about 10 to the 4 hertz, then this would be an indication of a BSM origin for said gravitation.
And one question on the inspirals, that those would be very short in time because they'd be only at the very end of the inspiral.
It depends how big the binary is.
Yeah.
So if it's at the merger phase, it's extremely short.
Yeah.
And DFDT is of order F. So it's extremely short for gigahertz.
Yeah.
But if you're in a very wide binary, then it's still very much in the inspiral phase and it can be relatively slow, relatively long-lived. Okay, another reason to go super kilohertz, and I'll go relatively fast through this, I don't need to explain each one in detail, is simply that we would expect there to be a number of different astrophysical foregrounds in the bands that we already know how to access experimentally. So this is PTAs, this is the future Lisa mission, this is LIGO, and what you see here are these various different curves indicating that there are expected astrophysical foregrounds. And if this is the measurement of the supermassive black holes, then that's already a measured astrophysical foreground that is stochastic in nature. And so if you have your favorite model that generates a signal that lies well below these astrophysical foregrounds, you're going to have a bad time trying to actually measure that thing because the data streams that you actually measure with these experiments is not sufficiently complex necessarily to allow you to do a lot of foreground subtraction. So maybe you have astrophysicist friends, in which case they're super happy and they're Buzz Lightyear. But if you're a particle physicist, then maybe you're Woody here and you're rather unhappy about the situation. Finally, the last and probably most mundane reason to think about looking at high frequency gravitational waves is that there are a large number of experiments that have been proposed to look for light dark matter, wave-like dark matter. And it turns out that the vast majority of these can actually also be sensitive to gravitational waves, even at the low frequencies where we have other technologies. And likewise, it's already been shown by many different groups that the gravitational wave experiments that we already have or that we will have can also be sensitive to ultralight dark matter, so the sword cuts both ways. But in any case, if you have an idea for a light dark matter experiment, chances are it's also sensitive to gravitational waves, so if you tell the experimentalists this, they're very happy to go and do a search in their data. Okay, so with that motivation in hand, let me discuss the basic assumptions that we're going to be making to be able to estimate the best sensitivity of the detector to gravitational waves. So if we have an incoming gravitational wave, as we all know, it causes vibrations, it causes ripples in space-time. So my gravitational wave comes in, it displaces these test masses, and I can think of the gravitational wave measurement as a displacement measurement. So maybe I go away and I ask my favorite AI chatbot, what is the best measurement I can do of a displacement? It's probably going to spit out something like this, which is the PSD for displacements at the so-called standard quantum limit. So your chatbot probably doesn't assume that you can manipulate quantum states of matter, and so it's going to give you this as the best possible measurement. Now you'll notice here that it seems as if I can take the mass to infinity and therefore make an infinitely good measurement, because that would reduce the noise power spectral density to basically zero. But we also know that the equivalence principle tells us that the mass of the system that is interacting with the gravitational waves should not be relevant to the signal itself, right? F equals ma, the F that you get from gravitational waves is proportional to m, so m drops out on the two sides of the equation. So why is mass appearing here, and what happens if we do take that mass to infinity limit? So when we make this displacement measurement and when we calculate what the standard quantum limit is, we're actually assuming another step, which is that we're not only measuring this displacement, but we're measuring it by imprinting that displacement on photons. So we're introducing photons into the system, whether we like it or not. There's always going to be at least the vacuum photons. And we're going to be measuring what those photons are doing in our experiment. And those photons themselves introduce what's called imprecision noise. So in fact, when you have the SQL, what you have is the imprecision noise associated to the measurement device, so the photons in this case, and the fact that they cause the force on the mirrors themselves, which is the back action force. And it's this piece that goes away when you take the mass to infinity, but not the first piece. If you wanted the SQL, you would balance these two out, because this gets better as you increase the amount of power in your laser, for example, in LIGO, but this one gets worse, and that's how you end up with the SQL. So when we take our mass to infinity, what we're really doing is we're setting the back action to zero, but we're left with this imprecision noise. And this imprecision noise depends on the photons that we're inserting into our device, and in particular, how many of them. So to give you a sort of example that you might be familiar with, here are the LIGO sensitivity curves, and I've traced out for you the back action noise and the shot noise, which is this imprecision noise, and I'm basically going to ignore all of this. And as you can see, that's a pretty good assumption, especially at high frequencies, which is where I'm trying to motivate was maybe more interesting to learn. Okay, so if we only care about imprecision noise, what this means is that what we only care about is the electromagnetic energy inside my detector, right? The photons in my detector and what they're doing. So before I talk about the noise, let me think about the signal. So the signal can also be imprinted on the photons, and we can get either a linear in strain term, which now I'm writing in the frequency domain here, or I can get a quadratic in strain term there. So if you're familiar with the way interferometers like LIGO work, you might be expecting that the only thing worth measuring is this linear guy. If you're familiar with Axion experiments like ADMX, maybe you're thinking that they measure power, but if they can, in principle, measure a linear in strain or a linear in whatever VSM quantity you're trying to measure energy, then why wouldn't they do that, right? Is the linear measurement clearly better? Anyone want to try answering? No.
You do the maximum?
Sorry?
You do the maximum, like the highest temperature.
We will see that they're actually the same. Okay, and so to show that, let's start with the detector that at first glance appears to be worse because it's quadratic in some small number. But I can do this measurement that's quadratic in some small number in a way such that my background photons, so either they're DC, let's say we've got a DC magnetic field, or they're oscillating at some very low frequency, so that in the frequency domain, that background number of photons is extremely far away from where my signal is. So my signal fields are at some frequency that is very, very far away, and therefore I'm doing a measurement in a regime where I have basically zero background photons other than the ones from the imprecision of the vacuum, so the 0-point photon, half photon, and the half photon from the back action associated to making the measurement of the zero photons in the first place. So if I'm in that regime, more concretely, what I have is a power spectral density associated to the noise of a single photon in the high frequency over temperature regime, or a temperature in the low frequency versus temperature regime. My signal, meanwhile, is quadratic in the small number strain, and obviously linear in the stored energy of my detector. And this whole thing here just tells me sort of how in frequency space my signal is spread out. I'm assuming just some sort of box with width delta omega. And importantly, I'm omitting what this transfer function is here, which we will see a little bit later. But if you plug this into your SNR, what you find is that for a classical detector, so this is something that is classical operating at the quantum standard quantum limit, then I get a minimum detectable strain that scales like 1 over the square root of the energy, some factors associated to bandwidth and integration time, and 1 over this transfer function. So the fact that this scales like 1 over the square root energy is not surprising. After all, this is a quadratic in strain measurement, but linear in the stored energy. So you might think that indeed a linear in strain measurement would do better than this. So now let's consider that linear detector. If I have a linear detector, it means that this 2-point function has to be non-zero, otherwise I'm not detecting it. But if that 2-point function is non-zero, that corresponds in the frequency domain to a cartoon that looks like this. So I have a signal and a background that sit on top of one another, but it also means that my background and itself have non-zero overlap in the same frequency band where I'm hoping to make a measurement. So what that means is that I actually have a large number of background photons hitting my detector, much, much larger than the 0 background photons that I had in my quadratic measurement. So in the end, what I have in this sort of linear measurement is a noise power spectral density that scales like the square root of the number of photons, assuming that I have some sort of Poisson distributed source of photons like a coherent laser, which I can rewrite as the square root of the stored electromagnetic energy in my detector. So this is the case, for example, for LIGO, where often you will see that the shock noise scales like the number of photons, or they may be re-expressed as the power in the laser. Meanwhile, my signal PSD is obviously linear in strain and in the stored energy, as you would expect. And what I find plugging this in is that the minimum detectable strain for a classical linear detector scales exactly the same way as what I found for the quadratic detector. So indeed, the people doing ADMX are not being stupid. They're doing a measurement that for their device makes a lot of sense. And the LIGO people are likewise doing a measurement that for their device makes a lot of sense. The question is, can we do better than this? Indeed, we can. And in fact, the best way to do better than this is to use a quantum limited, a beyond SQL, but still quantum limited linear detector. And the ultimate limit is the so-called Heisenberg limit, which requires manipulation of all of the photons. So you need to not lose a single photon in your measurements. If you know exactly what they're all doing, because they're all in a Fock state or they're all entangled, then you can reach this Heisenberg limit. And only then do you reach that sort of naively anticipated scaling of your minimal detectable strain with the stored electromagnetic energy, where it's just linear. There's some accounting of bandwidth factors and integration time there, and obviously the transfer function of your detector as well. But as I said, this requires absolutely no losses anywhere in your detector, so whether this is achievable or not, probably not. So maybe you've also heard about a different quantum approach, which is to insert so-called squeezed vacuum states into your detector. So this is something that's already done in LIGO. And if you remember the plot that I showed a few slides ago, that plot was actually from a paper where they demonstrated going beyond the SQL using squeezed vacuum states. But back in the 80s, Carlton Caves and Broginski realized that there was actually a limit to how well you could do with squeezed vacuum, which was not as good as the Heisenberg limit. And there you find that your minimum detectable strain scales like 1 over u to the 3/4. Okay, so those are the ultimate limits. Now let's just check that these totally basic assumptions actually reproduce what we expect from experiments. So you might consider interactions of gravitational waves with light. This is something that we considered first. I will skip through that because it's a little bit less interesting for reasons that will become more clear later on. But you can use our totally basic assumptions to calculate what the transfer function for an electromagnetic detector of gravitational waves would be, and then you can choose your favorite detector, figure out what regime it's in, where this is your signal frequency, this is some background frequency if there is one, and this is the gravitational wave frequency and the length of your detector L there. I will skip that because it's not so interesting. In the case of the interactions with matter, as I said earlier, the effect of a gravitational wave in a particular frame looks like this Newtonian force. So we see what I claimed earlier, namely that the mass appears both on both sides of the equation of motion, and so is therefore irrelevant. In this case, we can use our heuristics to derive the equations of motion in the frequency domain, the interaction of the gravitational wave with the displacement that is appropriately normalized here, and how that displacement is in turn imprinted on the photons in your detector. So you should have in mind a cartoon similar to this one, where the gravitational wave is causing a vibration or a motion of some macroscopic object, and this macroscopic object is bouncing photons around and therefore imprinting that motion onto said photons, precisely like LIGO. So speaking of LIGO, if we do apply our heuristics to its particular implementation, and you don't account for the transfer function, what you would find is that despite the fact that it has a seemingly large amount of recycled power, 350 kilowatts is nothing to laugh at, that would correspond to a strain sensitivity of 10 to the minus 12 per square root hertz, which is clearly not what LIGO actually achieves. So if we go away and compute what the transfer function is for LIGO, which operates in this particular regime, what we find is that that transfer function, or the square of that transfer function, is 10 to the 22. And so when you plug that back into here, you get 10 to the minus 23 per square root hertz, exactly as you expected, or as you already knew we should be obtaining. So this is just to say that our heuristics are not completely off base and give you a pretty good estimate of the sensitivity. So we can apply those same estimates to a work that I did with Valerie Domke and Nick Rod about a year ago, where we considered a sort of update to the standard Weber bar, where you have effectively a Weber bar, but it's also a great big magnet. And by virtue of being a great big magnet, it has an enormous amount of stored electromagnetic energy. And so away from the mechanical resonance regime, which is the one Weber bars were originally intended to work in. So if you're in this regime here, where a characteristic electromagnetic resonant frequency is much greater than the gravitational wave frequency, which is in turn much greater than the mechanical resonant frequencies, then you would expect that the 140 megajoules of stored energy in this magnet corresponds to a strain sensitivity of 10 to the minus 21 per square root hertz. Also different from that of LIGO. And indeed, you can then ask what is the transfer function. What you find is that you expect it to be about order 1, because everything here, there's no resonances involved. This is much larger than the omega, which is the omega gravitational. This cancels with this cancels with this, and so you expect a transfer function. And we confirmed that in detailed calculation in our paper, which predated the paper on the heuristics. So that was just to give you an idea of different types of experiments and how the heuristics work. How do they actually apply to detection or the prospects for detection of these stochastic gravitational wave backgrounds? We would like to be able to see. So if you're deeply unhappy, maybe you should leave the room now, because you're not going to get that. Okay, so we saw a couple of examples of detectors that measure strain with great sensitivity, less than 10 to the minus 20 in strain. That sounds great. Where's the problem? Well, the problem is that if you want to detect stochastic gravitational waves, what you're really trying to measure is an energy density, which for gravitational waves scales like strain squared times frequency squared, meaning that as you go to those higher frequencies, that at the beginning I was saying were sort of more interesting to look in because there were fewer foregrounds, well, it means you also have to probe smaller and smaller strains to measure the same large omega g when I normalize that energy density to the critical energy density of the universe. So if you put that on a plot, it does not look good. So here I'm showing you the n-effective bound as just a flat line, which is not entirely fair because it's a bound on the integrated abundance of gravitational waves, but it's roughly 10 to the minus 6 for that integral. Here you see the actual LIGO limits on a stochastic background with gravitational waves, and overlaid on it more or less is our heuristic estimate, which, as you can see, kind of reproduces their actual sensitivity. Likewise, the actual projected sensitivity of this magnetic Weber bar proposal, along with the lighter green, are heuristics, which match even better, which I think just points to the fact that we were quite aggressive with our assumptions for this darker green line in the first place. A different proposed experiment, Nego 2.0, which you can ask me about offline. The holometer, which if you don't know, was a device built at Fermilab, trying to look for quantum gravity effects. Won't comment on whether that was a sensible thing to do or not, but they did this experiment and they set these limits in the light blue, and our heuristics match it precisely, and then this is a different type of experiment. But what you can see is that most of these experiments, especially at high frequencies, are very, very far from even reaching omega g equals omega true, let alone the ineffective bound. Here I'm also showing a couple of sort of spectra associated to signals that would saturate the ineffective bound. It's actually very difficult to make something with such a large amplitude in practice. So you shouldn't take this as meaning, oh yes, there's definitely going to be a signal here. Rather, this is just to show that if you had a signal that was peaked at this frequency that did saturate the ineffective bound, you're still many, many orders of magnitude away from reaching it. So you might have thought, okay, I can add many, many detectors and improve my sensitivity that way, but then you would find your sensitivity to big omega g scales like 1 over the number of detectors. And so if you want to get from here to here, you're going to need 1 million of those. So what if we just took those concepts for classical detectors and beefed them up, right? Let's turn up the dial to 11 and see what happens. So if I took the entire stored electromagnetic energy of ITER, which is 8,500 cubic meters with about 12 Tesla applied across the entire thing, that corresponds to 10 to the 12 joules of electromagnetic energy. If I could operate that thing as a magnetic Weber bar, which I'm not saying you should or even that you could, but if you tried that, you would find this sensitivity here in the broadband mode. If you couple that to a resonant electromagnetic detector, like some sort of LC resonator, you could improve by a little bit. But you still see that in terms of the frequency reach that you have, below the ineffective bound, it's a relatively modest gain, despite the fact that you're harnessing an enormous amount of electromagnetic energy. So you might have thought then that the better thing to do would be to just take LIGO and beef that up instead, right? So 350 kilowatts got you this gray line. What happens if you increase the power? So yesterday I gave this talk at NYU, so it was pertinent that I had an NYC laser. So this is 10 gigawatt consumption, which is the peak sort of summertime. Everyone's running their AC consumption of energy of all of New York City. And if you didn't melt your mirrors, which you probably would, then you would get this sensitivity curve where I'm only assuming shock noise. So once again, in terms of the reach at the ineffective bound in the frequency domain, you're only really gaining about 1.5 orders of magnitude relative to current LIGO. And that's bearing in mind that I've assumed that I can get rid of back action noise entirely, which is not actually true.
Okay. Could I ask, for ITER is an empty space that has plasma, where your magnetic Weber bar is some solid metal?
Yeah, so I don't need the plasma for this. I just need the magnet and the volume.
Okay.
So I would argue that the only real or more realistic prospect for going to higher frequencies than what LIGO is able to probe is to actually harness quantum resources. So here you can do much better with much more modest amounts of electromagnetic energy. So in these green lines, I'm assuming either a broadband or a EM resonance experiment where I'm doing single photon counting. So this is neither at the Heisenberg limit nor at the vacuum limit. This is simply assuming that I can reduce the photon number of background photons to 0. If I use a 1 kilowatt version of LIGO at the squeeze vacuum limit or at the Heisenberg limit, then I can obviously do much, much better. So the point of this slide is simply to say that I think we should be investing rather in quantum resources rather than classical resources if we want to get to higher frequencies. So with that, and just a second after I was told to stop, let me leave you with some open questions, and I think the main summary of the talk here on this slide. Thank you.
Questions for Sebastian?
See sad face.
I guess not, well, but if you, so I would have thought you would need a huge magnetic field, but you showed that those are MRI sort of fields, like 9 Tesla
Yeah.
fields, so this is reasonable and those are way smaller than LEGO, so I have to think the cost would be way less too than.
Yeah, so here, these green lines are MRI style magnets. But the investment would be on the detector side. You'd have to use a single photon counter, which has such a low dark count rate that it's below the standard quantum limit. And here I'm assuming that there's a single photon signal in the entire integration time of my experiment. So that would correspond to these curves here, and this is broadband or with an EM resonant. Yeah, sorry.
Why don't you utilize white light instead and kind of do like a noise shaping as like the pseudo photon squeezing, but you're like squeezing out the errors in this case.
Yeah, good. So you can certainly use other states of light that aren't the two extreme examples that I chose here. So your example would be sort of going in the direction of, I guess, maybe going towards the Heisenberg limit, right? You're manipulating your laser in a particular way, so you know more about what the photons are doing. Whether that can actually reach the Heisenberg limit or not, I don't know, but it would sort of point in that direction. Yeah. So you can use other states. The point is simply that these quantum states of light can help you. And these are sort of the rapid lights that I'm solving with you.
Isn't it like the filter rather than the source? Because the source can be.
Yeah,
as long as
filtering
it's
can only
random.
do so much for you. So it really has to be at the source. So filtering noise out, you're still going to be left with intrinsic noise even in the frequency band that you want to measure. But that would be more like doing single photon counting after you filter those photons outside of the band where you actually want to do them.
All right, any further questions? Okay, since we're over, let's thank Sebastian again.